Yep. That way I know I won't forget. Okay, I hope I won't forget. Hey, Andrew, I can't see the technical difficulty screen behind you. I remember that. Was that from The Simpsons or something?
Yes, it was.
It was. Okay. It showed a drunk guy
Yeah.
with a bottle of whiskey, with a jug of whiskey or moonshine.
Yep, that was what it was.
By the way, I just learned that Zoom now has an option where under video settings, you can set it up to view a 7x7 grid instead of merely a 5x5 grid of people. I did not know that, which means you can put 49 tiny people on the screen at once. Which is actually kind of cool. Okay, let's see how my sharing works.
Honest mute or
eventually maybe, but not yet.
I got a couple of questions real quick if we can.
Okay. And if anyone has a cat that they'd like to put in front of the screen or a dog that they'd like us to say hi to, you can do that too. So go ahead, Gary.
When we take the exam, how much do they charge to take the exam? Do you know?
Did you get the info that I sent about that out of curiosity?
I just opened up the Zoom because I was so late, so I haven't had a chance to take a look at any of the other.
Okay. So it's $15 to take the exam.
Okay.
And then
Is
the
it
FCC
an online exam or is it exam at a?
you can do anything you want. You can go take an in-person exam if you have one near you, or you can, depending on what the class looks like. Let me see what it looks like as far as open seats in the exam session. Let me see. Friday exam. Let me just see. So far, there are 10 slots claimed out of 24. So there's plenty of room.
Okay.
And basically the way we do that is that you have to have 3 examiners overseeing an exam. And you need 2 video sources. You need your laptop computer and then some other computer, which is or some other device, which is typically an iPad or a phone with a camera on it with no audio, so that we can see you from the side and make sure that there's nobody else in the room, et cetera, et cetera, et cetera.
Oh, okay. I took my my agent exam for life agent here a couple of years ago and had to go to a site here, and we're in Texas. There's not a lot in Texas. I put in my zip code and said, are there any classes within 100 miles of me? And it came back and says, nope.
Well, I mean, but that's in person, I mean, there may be, it totally depends. Some clubs might do it locally. Like I have done many tests and classes over, online. I also did a whole bunch of them in person. And what I found was that in person is great, but you're limited in scope, which is fine. I mean, but you're limited in scope. I mean, I taught a class as small as 5 people once. And, I'm on vacation from work this week. So this is part of how I'm choosing to use my vacation time.
So now,
does that make me sick? Maybe a little.
Do you do this for just for fun, or do you make money at it? Or
well, how much did you pay to join?
Well, it said a nice round figure there on the sheet on the screen, so
yes,
that's what I choose to believe.
Yes, it's 0. I charge nothing. This is my way of kind of paying it forward.
Awesome. I love it. I love
So-
it. That's so good.
Good
This
morning,
is-
Scott.
Good morning. And this is like the third, I want to say the 32nd or 33rd class I've done in the last 7 or 8 years.
Wow.
So I do this because I enjoy it. I mean, if I weren't an engineer for a job, I would probably be, I would probably be a teacher, I think.
Oh,
Yeah.
okay. Scott, quick question.
Yep.
Can
Long and protracted answer.
okay. I can sign up for the exam even on 27th, 26th. I mean, sorry, 28th or 29th.
Yeah. So long as there's an open seat, sure.
Okay.
I mean, if you wanted to, if you after the first day, you're like, oh, I'm going to go take the exam today. You could do that too. Doesn't
Okay.
bother me.
Right. Okay. Thank you.
Mhm. Okay,
So
let's,
should I be taking some notes?
it depends. Depends how you study best. You know, a big part of this is the fact that I can only go so far. I can only teach you so much, you know. Really, it comes down to the fact that there's all these practice sites, practice exams, go Phillies. And there's like iPhone apps for studying, there's iPad apps for studying, there are computer-based apps for studying. And really what it comes down to is I'll give you the background. I'll give you all the, you know, the guts behind how this stuff works. But, you know, overall, it's really up to you to go and study and prepare yourself so that you kill the exam. You know, I can only do so much.
Now, I know I read it. It says there's like 35 questions on the exam, or is that?
Now, the tricky thing is that it's 35 questions on the exam. It's 35 questions on the exam, but the question pool is 400 something questions. Now, you will, you know, the way that the question pool is broken up, it's a certain number of questions from one area, a certain number of questions from another area, a certain number of questions from another area. So it's not like you're ever going to get, you know, 22 math questions, because that just doesn't happen. You know, that can't happen. That's not the way that the pool generates exams. It's not, you know, the FCC and the volunteer examiner coordinators have agreed that that's not the way it's going to work. The way it works is that, you know, they want to test your overall knowledge, and it'll be like, you know, 2 math questions and three band limit questions, and et cetera, et cetera, et cetera. So I recommend going out and getting yourself really ready. There's no time limit on the test. You can take it whenever you want. You can take it wherever you want. It can be on Friday. It could be 3 weeks from today. It could be 3 months from today. I don't really care. But what I would like to see is that everybody who starts this process, you can all do this. I have no doubt that you can all do this. It's just that, you know, you have to remember back, if you're not in school, you have to remember back to when you were in school and what studying feels like, and go back and study.
Now, another quick question,
Mhm.
because I'm gonna I have an interruption here, as I hadn't planned on this as we visited on the phone. And so I have a fellow coming to help me
Yep.
work on a project here at my house. And he's gonna get here about noon our time, which is gonna be about 10 o'clock your time.
Yep.
So how would I download your recording so that I can have the entire benefit of the class?
So when we're done, I'm going to sometime early this afternoon, my time, dump it all out, dump today's video on YouTube. And
Okay.
and then I have this massive link of everybody you see on this screen and then some. And I will be sending out that link, and you will all see the link, and you can click on it and go watch the video,
Awesome.
which will include exactly what I'm talking about. So, I mean, if you think about all the recursion, you can watch the video of me talking about the video, of me talking about the video, of me talking about the video, and so
Okay.
on and so forth.
Okay. So you're gonna send me a link?
I'll send everybody a link. I've got over 100 people on the list for this class, by the way. You notice that there's a lot of people here.
Where are they?
Can you not see everyone? If you go to upper right, you click on view gallery, it'll show the whole gallery.
Awesome.
All right, everybody ready to get started? Okay, well, I hope some people have done some studying. I hope some people have done some preparation. Even if you really haven't, that's really okay. It's better if you do, because then this stuff won't seem so alien to you. I'm Scott. My call sign is N7JI. I'm now older. I'm 54. I've had my license since I was 15. And I got into ham radio because I was introduced to it by my dad, who never had a license, but he had a friend who was a ham radio operator. And my dad almost, when he was a kid, got a license, but didn't have any money for equipment. So just decided, yeah, one of these days. And then one of these days never happened, but he got me into it. And so I got my license when I was 15, didn't do anything for a couple of years, then went off to college, found my college, University of Maryland Ham Radio Club, go Terps. We did a lot of activities together because ham radio is an activity of doing rather than just knowing. It's a very active thing. And we did a lot of contesting there at the club. I also became a volunteer examiner and gave exams on campus for, about the next 11 or 12 years while I lived there or around there. And then I moved to Oregon, got married, kids, work, et cetera, stayed active, but not as active. And then as the kids became older, my kids are now 14 and 20. My younger one is K7 NAR. My old one is W7 HER. My younger one, with a little urging, is the president of his high school ham radio club. My older one is the president of the University of Oregon Ham Radio Club. Again, with a little nudge, it's a good thing to do. And I'm gonna hide my video here to give you an idea of where this all started. Can everybody see me? Okay, yes. Can you see the little kid there? All right, that's my daughter when she was 6 months old. That was during sweepstakes in 2001. 2001? No, 2002. That was sweepstakes 2002. She's turning 21 this year. And that was her at 6 months. And my wife took that picture of her eating my microphone. So anyway, ham radio in my family goes back a long way. And at some point I just thought, I really like teaching this stuff. Maybe I should just teach it. And so, 7 years later, here I am. And 7 years later, here you guys are.
Appreciate you.
Yeah. Okay. So the next question we ask is, what is ham radio and how did it come to be? So what I'm going to do is share this little thing on the screen. And everyone see this? This is a good test of our video sharing. Can everybody see?
Yes.
Okay, so after Maxwell discovered Maxwell's equations and predicted that electromagnetic radiation would exist and that we could actually send energy wirelessly, Heinrich Hertz, you may notice that name, Hertz, unit of frequency, commented in an interview that he was doing or a class, "I do not think that the wireless waves I have discovered will have any practical application." And that was in the late 1800s. So anyway, I would be the first to say I think he was wrong, but he was a scientist, not an engineer, so it really wasn't up to him to figure out what we were going to do with these wireless waves, which everybody uses today. And you can all thank, if you're on a Wi-Fi connection, you can thank Hertz for discovering them, even though he thought that they would be practically useless. Okay, so shortly after that, we have this thing called ham radio. Well, ham was kind of an insult, it's thought of, by telegraph operators who considered the amateurs, who really didn't know what they were doing because they weren't professional, to be the ham-fisted folks who were not professional and just sort of like hacks. And so it is thought that ham radio was kind of kind of an insult. And of course, we took it as, okay, fine. They want to insult us. That's fine. So we became ham radio operators. In the early 1900s, in the Wild West of radio, it was determined that radio waves would do weird things like bounce off of the sky. But that really wasn't done very much. And it was kind of hard to generate frequencies that would bounce off the sky. And so the military decided, well, you know what, we're going to use all of these frequencies for long range communications. And we're going to set the limit at 200 meters in wavelength, which we'll get to very shortly. And we're going to basically say that all those wavelengths longer than 200 meters, we're going to find something useful for. And you guys can, practice with those useless waves that you can't generate yet. Well, as it turns out, joke was on them, because those waves that are 200 meters long and longer they do bounce around the world quite well, but they require some pretty big antennas. And so it was up to the amateurs, the hacks, the makers, the people who were goofing around with radio to figure out, oh, well, if we make these higher frequencies, which is why they're known as high frequency or HF, those are the ones that if we can make them, will bounce very, very long distances off the sky, using the ionosphere, using the atmosphere to bounce waves thousands and thousands of miles. So those became the amateur radio frequencies. And then after World War I, after radio proved itself to be invaluable, and all these operators who were basically pulled out of the amateur ranks had proven their worth on the battlefield, as being something that would actually turn the tide during a war, it was determined, okay, you know what, let's codify this whole thing and let the amateurs keep their frequencies. So here we are 100 years later, we still have those frequencies available to us. We have frequency bands and we pay absolutely nothing for them, which is kind of amazing, considering that, there aren't many things around these days that you don't pay anything for. And you essentially pay almost nothing to use these frequencies and to keep these frequencies. And for those of you who have some idea of what the FCC has done in the last 20 years or so with regard to licensing of different frequencies to different services like cell phones and things like that, cell phone companies, these frequencies that we have access to are worth billions and billions of dollars. So it is important to think of these things as kind of like the national park of radio, where we, by virtue of the fact that we know what we are doing and we're not going to hurt anyone, are allowed to use these vast ranges of frequencies. They are basically assigned to us with the knowledge that we're going to use them for something good. Okay, so what is that something good? Because you truly don't get something for nothing. That doesn't exist. So can everybody see this? Okay. Everyone see this? Okay, this is the FCC Part 97, the rules of the amateur radio service. This version is maintained by the ARRL, which is our United States National Association for Amateur Radio. It's a member organization that represents amateur radio in front of Congress and the FCC and things like that. Some people complain about the organization because it's largely volunteer, but they're our voice in front of the government. So essentially advocating for us. Part of this is, notice all these rules, right? Notice you don't have to remember all these rules. All you have to know is that if you have any questions when you get your license, you can always go back to these rules. And thankfully, it's a searchable file. So you don't have to know, you don't have to look through everything to find what you're looking for. Most importantly, though, notice these basis and purpose. There are 5 reasons that we exist. Number 1, voluntary non-commercial service. So basically, it doesn't cost us anything. We also can't make anything, particularly with respect to emergency communications. Number 2, contribute to the advancement of the radio art. Believe it or not, there's still a lot of stuff happening with radio in in the past 100-something years, things like single sideband that we take for granted, things like spread spectrum that we take for granted now, a lot of digital communications that we take for granted. Ham radio operators were the ones who were kind of on the cutting edge. And believe it or not, we're still actually doing a lot of cool things. The fact that we are using the internet right now, it basically uses a version of the AX.25 protocol, which was invented by hams for packet radio. So the communications method that we use over the internet is essentially a variant of what was developed for ham radio. Encouragement and improvement of the amateur service through rules which provide for advancing skills in the communication and technical phases of the art. That means it's a good idea to learn how to solder. It's a good idea to learn how to lay out a printed circuit board. I would say that also includes learning how to program, learning how to make sure that your new Arduino can do something cool. It means communication and technical phases of the art. That means that we know how to get on the air and operate. That means we know how to build cables and make them connect together and understand what an antenna is and why an antenna is a particular size and shape. Expansion of the existing reservoir of trained operators, technicians, and electronics experts. Believe it or not, a lot of people are not trained operators, technicians, and electronics experts. So you do not have to be technical in nature to do this. You also don't need to have gone through formal training in electronics, although some people have. I mean, I'm an electrical engineer, so this is kind of a no-brainer for me. But ham radio, amateur radio, if you look at the root of the word amateur, it comes from AMAT, which is Latin for to love something. So those who love radio, who do it for fun, who do it for the enjoyment, become experts and at least cognizant and knowledgeable in the operation. And finally, continuation and extension of the amateur's unique ability to enhance international goodwill. There are roughly 3 million amateur radio operators who are licensed around the world, about 750,000 of them in the United States. And we are a group of people that by and large tries to remain apolitical. Now, independent of what our countries are doing, what our governments are doing. This is a hobby that is a worldwide thing. And it's a service, and part of the service is international goodwill. So when you're on the air, part of what you're doing is establishing international goodwill. I have had many conversations on the air with people from before the fall of the Iron Curtain. For those of you not old enough to know, the Iron Curtain was basically the Soviet Union and all of its member countries, as well as all the adjacent countries like Bulgaria and Yugoslavia and Czechoslovakia and Poland, East Germany, that were behind the Iron Curtain. When I went for my first job, when I went and got my first job out of college, one of the things I had to do was a security briefing. And I had to get a security clearance. And they said, do you have any contacts with people who are who live in hostile nations? And I said, yes, I talk with them all the time. And they said, well, what countries? It's like Czechoslovakia, Bulgaria, Romania, Hungary, Poland. And they said, well, how do you know them? Like ham radio. And they said, oh, you're fine. Because there's an understanding that, you know, that is why you're doing this. It's for international goodwill rather than, you know, you're a security risk. Okay. So let us move on to the next thing. So that's why amateur radio exists. That's how we fit in. Okay, why do we have to learn anything that we're doing? You know, what is the purpose of learning all of this stuff? Well, okay, the next slide I put up is going to be, let's see, electromagnetic spectrum, band plan. Okay, we're going to put up the band plan. Now, remember when I said that we basically fit into, like, we're like the national park of the electromagnetic spectrum. We're going to get into the electromagnetic spectrum. All of these are frequency bands that amateur radio operators pretty much around the world can use. And notice there are many of them. These different frequency bands are at different places on the electromagnetic spectrum. They all behave differently. Some of them are point to point, line of sight. Some of them, the signals are sometimes line of sight, but sometimes bounce off the ionosphere and go long distances. And some of them, they basically bounce off the ionosphere and go long distances all the time, depending on the season, depending on the time of day, et cetera, et cetera. So it is our job, if you think about the national parks, to keep them clean. It's also our job with the national parks to go out and use them, or else, if nobody goes to them, they could be reallocated as something else. So you get your license, you get on the air, and you get to play around with all these things and learn and learn and learn. Now, the other thing is that this chart that we see actually falls into, this is why I say, let me wait for this to open. It's coming up. There we go. Okay, where's the NTIA document? There we go. And this is quite large. And it's not working, is it? I crashed it. Okay, I'm gonna have to open it again. Anyway, oh, now it's open. Great. There we go. Okay, can everybody see this okay? No, there we go. Okay, so believe it or not, all of those little frequency slots that we saw fit into this. This is the world of the electromagnetic radio spectrum. And somewhere, wherever you see this little section that is teal, that says amateur or amateur satellite, those are frequencies that we are allowed to use. So notice they actually are slotted in there in that giant spectrum chart with many, 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 many other things. Those are broadcasting, those are various communications for business, those are different satellite systems, et cetera, et cetera. So if you think of the entire world of radio as this, and television and cell phones and everything, that fills in this entire spectrum. We have these tiny little slices that it's our job to use and keep clean. But they're all over this chart, which allows us lots and lots of different things. For instance, there are a lot of people out there right now who, let's say we look at this particular frequency band over here at 5.8 gigahertz. And notice this says amateur right there. This actually is right adjacent to and actually partially overlapping with something called FPV drone systems. So if you fly a first-person view drone, it actually uses multiple different channels in this 5.6 gigahertz range. If you happen to have a ham license, you are allowed to use the frequencies that actually fall outside of the unlicensed service and in the amateur service. And there are many more channels available to you. So that's why a lot of people who have drone licenses also have their ham license, because with a ham license, you can operate in a larger range of different frequencies. So anyway, that is a basic view of the world of radio. And so the other question is, why do we have to learn everything that we're learning? What I just want to grab a radio and I just want to push the button and talk to somebody. Well, that's great. I don't have a problem with that. But the fact that, let's say that you get a driver's license, and the driver's license, you say, well, I'm only going to drive my little, I'm only going to drive my little Honda Fit. It's a tiny little car. Well, does your driver's license allow you to drive a Ferrari? Yes, it does. Does it allow you to drive like a rental truck that's not above a certain size? And the answer is yes, it does. So the license conveys far more than just operating in a certain range of frequencies. In addition to that, obviously you can, when you press that gas pedal in a Ferrari, you can go a lot faster than you can go in a little Honda Fit. And it gets there a lot faster. So we can sort of take an analogy there and say that, you know, let's say we have a 100 horsepower vehicle and we have a 700 horsepower vehicle. And we have a handheld radio, which let's say we have it set to transmit at 1 watt of power. We can also, on that same set of frequencies, hook up a radio to a big amplifier and a really big antenna, and use that same set of frequencies to aim signals at the moon, transmitting with 1,000 watts of power with 30 decibels of gain with a big dish antenna, and have an effective power of 1,000,000 watts aiming at the moon, which is perfectly legal. You know, it's actually covered by your license to do that. And that's why we need to get a license. And that's why we need to study this stuff, because if you have effectively the equivalent of 1,000,000 watts of transmitted power, what can you do with that? Let's hear some of the things that can happen transmitting with 1,000,000 watts of power in one direction. Come on, some guesses from somebody. I also like to be interactive. So if you have an answer, just spout it out.
As a DJ, I would have to say you're gonna blow somebody's ears.
Well, but it's RF. It's radio frequency. So you aim 1,000,000 watts of radio frequency and it points at somebody.
Are you talking about blowing up the moon?
No, we're talking
Oh.
about bouncing signals off the moon.
Just checking.
Yeah, but what happens if somebody happens to get in that beam of 1,000,000 watts, equivalent to 1,000,000 watts of energy?
You
You
drown
blow-
out other people?
Well, yeah, you can also, like, you know, cause some serious injuries.
Fry 'em.
Yeah. So does anyone know how a microwave oven works?
I do.
Do you? Let's hear it.
Well, there's a bunch of heaters inside the microwave. And well, I think I know. There's a bunch of heaters inside the microwave, and there's basically this kind of motor in it, and it spins the food around, heating it up, basically.
Okay, that is more
That's
of a
kind
that is more of a convection oven.
A microwave would be more of a, the signal, the waves are moving so quickly that they actually make the meat or whatever's in the oven cook, because it's causing microwavy friction, moving the molecules so fast.
Close. That's closer.
Is
Okay.
it true
It
that,
uses a magnetron,
It uses a
and
magnetron. Yep.
yeah, to emit the proper radio frequencies using, you know, the electricity using the magnetron,
Yep.
and
Okay.
heating up the water and the
Yep.
grease in the food.
Okay. So we have our H2O molecule right here, which has a resonant frequency of about 2.4 gigahertz. We're going to talk about resonance too. And we're going to talk about giga, and we're going to talk about hertz very shortly. This also has a wavelength of about 12 centimeters, which we're also going to get into. Again, that's why we're doing all this. So if you look at your microwave oven, what it is essentially in the side is a radio frequency transmitter with about 1,000 watts of power at 2.4 gigahertz, which is why sometimes if you turn your microwave oven on, you might actually lose your Wi-Fi signal because they share frequencies, or very, very, very close to those same frequencies. You have a radio frequency transmitter at 1,000 watts. That energy basically travels into this big cavity, and inside the cavity, you have oxygen, hydrogen, hydrogen, oxygen, hydrogen, hydrogen. My apologies to Mickey Mouse. Oxygen, hydrogen, hydrogen floating around in there. And this frequency is very close to the resonant frequency of the water molecule, which causes the energy that's being transmitted to cause these atoms to shake violently, the molecules to shake violently. And shaking and motion is the same thing as heat. So you basically heat up the things that are full of water. which is why if you put something in there in the microwave that has no water in it, that it's all dried out like ceramic, it doesn't get particularly hot. But the water, anything with water does. And for instance, that's why if you stick an egg in the microwave, it'll cook the inside of the egg, but not the outside of the egg. And I don't recommend doing it unless you plan on cleaning up afterwards.
Hey, Scott, I got a question for you.
Yep.
What device would you use to measure microwaves?
When you say measure, how do you mean?
Just intensity and even location tracking from a device, if so.
Well, I mean, a microwave is basically just a radio frequency. I mean, if you're looking about the microwave energy, it's just a radio frequency. And really, I mean, you basically have the equivalent of a 2.4 gigahertz receiver. But I mean, you don't particularly care to listen to it. You just want to measure signal strength. So essentially it's just basically a tuned circuit with an antenna that is designed to pick up that frequency. And instead of listening to it, you'll use it to convert into movement of a meter that shows, that shows energy, energy density or.
So a logarithmic wideband, would that be sufficient?
What, antenna wise or receiver wise?
Yes.
Probably. Probably depends. Well, okay. What's the frequency of a microwave oven? 2.4 gigahertz. All right. Anybody know the speed of light? Gonna get into this.
186,000 miles per second.
Or 300 million meters per second, or 3 times 10 to the 8th power meters per second. That's the speed of light. And we have our frequency of 2.4 gigahertz, and giga means billions. So 240000000, and hertz is a unit of frequency. And by combining this and this, C F lambda, our formula is C equals F times lambda, where this is our frequency. And this is our wavelength. You've naturally caused me to move into our first section. The formula C equals F lambda. C is the speed of light, 3 times 10 to the 8th meters per second. And very often our frequency is measured in megahertz because we don't really need to know the exact number of hertz. And because of that, we actually just make this 300. We get rid of the mega. And what we end up doing is saying, okay, 300 is equal to 2.4 gigahertz, which is 2400 megahertz, times lambda. Lambda is about 12 centimeters. So the question is, how do we build an antenna that receives 12 centimeters? We're going to get into this as well. Let's say that we have oops, didn't mean to do that. An antenna that's a half wavelength long. A half wavelength is a perfect antenna for most purposes. That translates to somewhere between 5 and 6 centimeters. So if your logarithmic antenna can receive, has an element with a length of 5 to 6 centimeters, then it's a pretty good chance that it's going to work.
Great, thank you.
So somebody asked once when they came into one of my classes, are you going to teach us to use a radio? And my answer is no, I'm not going to teach you to use a radio. What I'm going to teach you to do is understand everything that's happening behind the fact that you're using a radio that makes it work in the first place. And then using a radio will be easy. Okay. So I know not everybody's going to want to not everyone's going to want to introduce themselves, which is fine. If you'd like to introduce yourself, let's hear it. Unmute yourself and just start talking. Let's see who gets in first.
Hey, how are you? My name is Michael Owens. I'm here in New Jersey. My brother lives in right outside of, I guess it's Lynchburg, Tennessee, and he was really involved with ham radio. I was involved with CB radio back in the day, and I used to make him cringe when I used to talk about the different things, like, you know, with the CB world. And he goes, you don't do that with the Roger Beep. You know, so he got me more involved with the ham radio and different antennas he's built and radios and so on and so forth. And he's got me heavily involved in this. So here I am today. And I'm really thankful that you're teaching this class on your time off. I really appreciate it.
Excellent.
Hi, Scott.
All right. Yep.
This is Pramotesh Desai. I'm in New Jersey. My son is a rally driver and a rally fanatic, and I have been going with him since his age of 2.5 to the rallies. I took him to the rallies way in Dubai, and that's where they use all the time ham radio. And now that I'm going to accompany him in his car, he wants me to learn about ham radio. So here I am, and thank you
Good.
for taking this course.
Cool. All right.
Oh,
Who
hi.
else? Yep.
I'm
Go ahead.
Clarissa. I'm a co-driver in a rally car. It's a good segue, by the way. I'm just trying to get my license so that we can have our own radio in the car, because we don't always have a little rally safe computer in there. So it'd be nice to have, you know, another method of communication in case something happens. That's about it.
Yeah, hey, Scott. Oh,
Yes. Go ahead.
Okay, sorry, I'll let you go next. My name's Anders. I'm in Anchorage, Alaska. I just graduated with a degree in mechanical engineering, working up here. And I had a bunch of friends who are electrical engineering students, and they, you know, I was talking about, they did like ham stuff, and I really regret not doing it. So as soon as I saw, you know, that you were doing a class, I decided to sign up just to kind of for the fun of it, basically. I don't really know what I'm doing yet, but I'm sure it'll be quite fun, whatever the journey takes me.
And the math stuff will be easy for you.
Yeah, hopefully I haven't forgotten too much.
Yeah. Next.
Hi, I'm Bree. Hi, my husband's the one that got me interested in it. He's actually ham radio. He's Kane 6 IOK right now, and he's actually trying to get me so we can go out into the field and do all that. So I'm really glad you created a class, because I couldn't understand what he was trying to explain. But I'm really grateful that you brought this class up. Thank you so much.
Okay, I see Betty's hand up next.
I'm Betty Meadows. I'm in 5th grade, and about a year ago, I wasn't able to go to school, obviously, so I decided to learn Morse code. And at the math festival in Oregon, I live in Oregon, the math festival, I saw a Morse code stand run by Scott, and I went up to it and found out about this class and decided, hey, I might as well do that.
Cool. Good way to use spring break. At least part of it. All right. Anybody else?
Yeah.
I see Gary.
Yeah. Anyway, we went to a preparedness fair on Saturday at a church, and they got me interested because I've always been interested in ham radio. 55 years ago, when I lived in South America, we would look for 5-element beams on the top of roofs so we could call home. Anyway, I would really like to be able to be a ham radio operator, so that when there's some kind of disaster, I'm in Texas, when there's like a hurricane or something, I can be of some kind of help to my neighbors. And that's something that really kind of excites me, is to be of some kind of service to my community.
Now, one thing I will say is that there are a lot of people around here, because we're in Oregon, and believe it or not, Oregon is an earthquake zone. You know, it seems really quiet most of the time, but every 500 years or so, there's a really big earthquake. So we're kind of waiting for that happening. And there's a lot of emergency preparedness preparation going on out here. And part of that is that if you stick your radio in the drawer, even if you keep it charged and you think you know what you're going to do, when an emergency happens, you are sadly mistaken. It's something that, you know, like any skill, the way to get good at it and the way to be comfortable with it when something happens and you actually need it is to practice, practice, practice. And part of what we do is practice, practice, practice. Every time you get on the air, every time you talk to somebody, Every time you participate in a net or anything like that, that's practice. And that gets you that gets you better at understanding how to operate, when to operate, how to how to interoperate with a larger group of people that's trying to serve a common purpose. But yes, actually, I do know exactly what you're talking about. And I actually have had, in my teaching, I've had many people who were interested in ham radio when they were in high school, and then school and girls and cars and college or job and kids and everything got in the way. And now they're in their 70s and they say, I actually want to do ham radio now that I'm retired. You know how many times I've heard that story? It's happened a lot of times. All right, somebody else was next. Was it Tracy? Did you have your hand up?
Yeah, hi, Tracy Hyatt. I'm in Pennsylvania.
Go Phillies.
The largest reason that I was getting involved with ham radio is similar to a lot of these other rally racers. I actually am involved in race organization, and we have found over the years that our ham radio operators are kind of dropping off and dwindling. As well, for emergency preparedness as well. My husband is a ham operator. I've actually been out on rally courses as a medical sweep and have used his call sign while he's driving. So we could communicate with emergency crews as well as hospitals and helicopters.
It's really interesting that that there are that many people who are interested in rally racing and outdoor pursuits in this group. That's really cool. One of the big things that we do locally in Eugene is that there's something called, it used to be called the Cascade Cream Puff, which is a long bike ride up in the mountains. And we have these things called the Cascades, which, the cell phone coverage is basically nil in most areas. We also have another one called it's up outside of Oak Ridge, and it's a 100K road race, foot race through the middle of nowhere. And so we provide communications. It takes 50 licensed hams to go out and provide communications for something like that. So anywhere where there are, areas that are off the beaten path, it doesn't really pay for cell phone companies to put towers up in areas where there's basically nobody. I mean, that's just economics. However, we can go anywhere we want and take a radio with us and provide backcountry communications. We can provide communications from point to point, to set up temporary repeater systems, and do all kinds of cool stuff. All right, who else wanted to go? Pablo.
I'll join the other rally people. I participate and help organize a 5,000-mile rally across the Arctic during the middle of winter. And we use VHF communications for emergency purposes. So I'm getting my license.
I have never had a group that was this interested in rally racing. Every time is different, Every class is different. Who else?
Juliet.
Yep.
I'm Juliet, and I am a scout leader with the BSA, and I have a few scouts in this group as well.
Are they gonna do the merit badge with me?
I think they would love to.
Okay, so they got to get their blue cards going, right?
I've got blue cards for them.
Okay, good. I'm also a merit badge counselor, so. All right, anybody else?
My name is David, and I'm going to join the emergency group. I live in Savannah, Georgia on the coast, and I would like to get involved with ham radio to help in an emergency, help my neighbors, and bring clarity and help to people using these skills.
Cool.
Hi, my name's Cass. I'm an active member of the Portland State Aerospace Society. I am an electrical engineering student, and I'm building nanosatellites that use amateur radio to communicate from orbit. So it's very important that I get my ham radio license. I'm really excited to be here. Thanks for holding this class.
And that's ORSAT. Are you guys working? How's it coming on the selfie stick? the 220-mile
going-
selfie stick?
It's going well. So right now we're working on a prototype that we'll be launching in July with SpaceX. We're putting up a 2U satellite, and then we have a little Schmidt-Cassegrain lens for the actual Orsat Live. I just applied a film of aero glaze paint to the outside, and we're going to start taking images with it soon. I'm really excited.
So are you going to be going to Seaside with us?
I don't know.
In June?
I don't know what that is. What's
Seaside
happening?
is the CPAC ham radio convention in Seaside in June.
Oh, fun. Yeah, I'd love to be there.
Talk to Andrew about going, because he was putting people together to man the booth.
Cool. That
So
sounds awesome.
I'm also involved with the collegiate amateur radio program through the ARRL. And that's one of the things we're trying to put together is a group that, in addition to PSAS, we kind of like partner with to go up and do have a table up there at the show.
Nice.
Usually gets about 2,000 people.
Wow, that's a lot of people.
So go talk. Make sure you talk to Andrew.
I will.
You can bother him over spring break. He doesn't care.
I love to bother Andrew.
I see Amber's hand up.
Hi, I'm Amber. I'm from West Virginia, and I'm interested in learning more about the ham radio so that me and my family can do more adventures together and be in more remote areas. And it's actually Dave's fault too that he got me into this. So yeah, looking forward to the class. So thank you.
Good. Okay. And was there anybody else? Susan.
Sorry, I was trying to unmute. My name is Susan Neiman. I'm in Gainesville, Florida. I am not a merit badge counselor or a scout leader, but I am the mom of 2 scouts. And I had a friend who was moving across the country and gifted me with her dad's entire ham radio setup.
Oh, you better learn how to use it.
Well, it all just looks like boxes of stuff to me right now. So that's why I'm here, is to figure out what's in the boxes of stuff and hopefully be able to teach it to scouts at some point. Although I'm still going to leave the merit badge part to you.
Okay. All right. Jackie. And it looks like Cooper.
So I am a Boy Scout from Troop 60, and I'm currently just mostly taking this class for the merit badge and my license.
Okay.
Yeah.
All right, cool. Anybody else before we really get into the meat?
I'm gonna physically raise my hand.
Go ahead, Brian.
My name is Brian Dallas. I used to work as the marketing director at Dirtfish Rally School, another rally person. And I'm going to be working support at Oregon Trail as well as Olympus Rally. So need to get my ham license. But on a side note, I work for a satellite communications company that does personal satellite devices for the public. So outside of ham, we also do two-way communications, so forth. The name of the company is Spot, by the way, in case you were curious.
Okay.
Yeah.
Cool. Anybody else before we really get into the meat? Go ahead. Is it Jacqueline?
Yeah, this is Jacqueline. That's me and my daughters, Phoebe and Naomi. We're taking the class because a friend, an Elmer of ours, introduced us to this class, and we were interested because we went to a rally nearby, and my husband is an audio guy. And when he talks about frequencies and things like this, we have absolutely no clue. So I thought it would be helpful, and so we can just communicate with people around the world too. We have friends and family around the world that have this stuff. So that was fun. Good idea.
Got so many rally people today. This is nuts. Go ahead, Chris.
Yeah, can you hear me okay?
Yep.
All right. Well, this is my second Zoom meeting. I kind of struggled to raise my hand and had difficulty getting my Bluetooth to connect the headset. So excuse me for my lack of skills on the PC. I'm in Fairbanks, Alaska, and I spent a number of years at sea as an able seaman. Done some radio work with Ski Patrol and other agencies, and my general radio operator's license expired years ago.
You had a growl. Wow. You actually had a grawl.
Oh, I think so.
Yeah.
It may have been a technician. Yeah, like I said, it was years ago. It was part of our Maritime Academy down in Seward. And yeah, so I'll have to turn the lights back off. I'm on my second cup of coffee, and look forward to all the instruction. Thank you.
Okay. All right. Anybody else before we go? Okay, here we go. So the first thing we're going to do, and welcome everybody. All right. The first thing we're going to do is we're going to start with this. And I don't like the way I drew that right off the bat. There we go. That's more circular and it's more centered. All right. So this should be a circle. And what we're going to do is the first question. And by the way, if you know the answer, just blurt it out. How many degrees are in a circle?
360.
360.
Right. And by definition, our 0 mark is over here on the right-hand side. So we go this way around the circle. And what we do is we start at 0, and then we get up to here, and that's 90. And then we get over to here, and this is 180. And we get over to here, and this is 270. All right. So what do we call the place where we started if we keep going up? Notice we're back at 360, but what's the other name for 360?
0.
0. Okay. So basically we went one complete loop around the thing. Now we're going to make this circle a very special circle. We're going to make it something called the unit circle, which has a radius of length 1. And so because of this radius of length 1, we can do this. We can make this a right triangle, and we can call this X, and we can call this a Y. And does everyone remember Pythagoras' theorem? X squared plus Y squared equals Z squared for a triangle. Well, we have our Z in this case is 1. So we have X squared plus Y squared equals 1. And these are actually very special terms. And the reason that they're so special is because we have these terms X and Y, and they have special names that relate to the angle theta that I've drawn there. And let me grab a rock or something and prop up my iPad so it doesn't shift around. There we go. Okay. Old and new technology. I'm propping up my iPad with a rock. Okay, so we have these special terms. X is equal to cosine of theta, and it's actually related to the radius, which is 1 in this case, so that goes away. And Y is equal to sine of theta. So we have to unfortunately start with a little bit of trigonometry. So these are known as sine and cosine. Here's our X and here's our Y. And there's actually a reason why we're doing this. Well, we also end up being able to substitute those and say that sine squared plus cosine squared equals 1. That basically means that for any angle that we pick, we end up on the circle somewhere. And what's cool about that is that it doesn't matter if we're over here or over here or over here. Whatever that angle is, we're somewhere on that circle. We're always 1 unit away from the center point. So what this allows us to do, however, is that those values of X and Y allow us to say how far to the left or right we are, and how far up or down from the 0 line are we. So how far left or right, again, that's known as the cosine of the angle. And how far up or down, that is known as the sine of the angle. And as the angle goes from 0 all the way around to 360, you'll notice that it goes back to where it started, which means it obviously repeats. And it repeats every 360 degrees. So now if I were to take something like this, and say that we're going to start at angle 0, and here's angle 180, and here's angle 360, and continuing on forever. The highest point that we're going to get to, if we look at, let's say, the sine, and again, the sine is how far up and down we go. What's the highest point we're going to get to, everybody?
90.
Well, no, what's the highest
1.
point? We're going to get to 1. We're going to get up to 1 right here. And what's the lowest point we're going to get to?
0.
Well, we'll get to
-1.
0, but then we're actually going to go to -1. This is +1, and this is -1. So we're going to get down to here, and then we're going to be on the horizontal line at this point, and at this point, and then back here and back here. And that is distance 0 from the horizontal line. So we're going to have a 0 there, and a 0 there, and a 0 there. And now we just connect the dots. And what is that called? That has a name.
The wavelength.
Sine wave.
That's called a sine wave. Now, so this is really tied into something that we see in nature all the time. Can anybody think of anything that spins?
Top.
Yeah. Earth. Yeah. Planets. We have planets that go around the sun. We have things that spin on their axis. We have, let's say that we look at the Earth, and the Earth has a tilt as it travels around the sun, right? So here's the tilt of the Earth as it travels around the sun. And it goes around in circles, which means that the tilt goes up and down and up and down. And it turns out that since we're looking at that and everything is circular, that the seasons go in a sine wave pattern as well. So if you notice the length of days, it doesn't go all the way down up to 1 and all the way down to -1, but the length of days actually looks kind of like that. And the reason it does is because motion is circular. And you might notice that this is called summer, and this is called winter, where you have longer days in the summer and shorter days in the winter. And you'll notice that when you get to the top, when you get to June 21st, your days are not getting any longer, but they're not getting any shorter either. And in winter, they're not getting any shorter, but they're not getting any longer right at that time. So that also means that when is your maximum change? It's actually right here. And this would be between summer and winter, and that would be September. And then there's another one that happens, but it doesn't actually show up on this graph. The reason it doesn't show up is because we haven't continued the graph. But since it goes on forever, as long as the Earth keeps going around the sun, we're actually just looking at a little snapshot of it. And you can also see that right here, the days are getting longer really fast. So this is known as March. So this is a practical application of something called a sine wave. Now, this is a really long sine wave, because how long does it take for this thing to happen? If we're looking at the seasons?
A year.
1 full year. So that wave takes 1 full year to happen. So that's a really slow process, right? So what does that mean? Well, if we were to take a look at our picture right here, that would basically be, this is the Earth going around the sun in the middle, right? So we'd actually be looking at a picture of the Earth going around the sun from above. Now, we could also be looking at something else happening instead of that. We could be saying that, let's say we are a car going around a racetrack. And that car going around a racetrack takes a minute. So we're going to erase some of this stuff. And now we're going to have a car going around the track. And it takes 1 minute. So in a period of 1 minute, how far this way do we start if our starting line is over at the 0 mark? And we're going this way around the circle. So how far from the horizontal line are we? At the starting point, we're at 0. After 15 seconds, we are way up here. So at 15 seconds, how far from the 0 line are we? Or from that
90.
horizontal line? We're 1 unit away. After 30 seconds, we're over here on the left. And we go through the horizontal line. At 45 seconds, we're down here. And at 60 seconds, we're on the 0 again. So how long does it take for this wave to happen?
1 minute.
1 minute. Well, okay, so that would be a frequency, or that would be a period. We'll call it a period. In this case, it's 60 seconds. How long was that period for going around the sun?
1 year.
It was a year. Yeah. So which one is a more frequent occurrence, in your opinion?
The second one.
The second one, right? Because the first one only happens once a year. This one happens once a minute. So as our period goes up, our frequency goes down. As our period goes down, our frequency goes up. So these are somehow inversely related. Okay, so now instead, what we're going to do is I'm going to erase this and do a new circle. Okay, we're going to have the same basic circle. We're going to start over here. And now we are going to have our 0 and our 90 degrees and our 180 and our 270 over here. We're going to go around this way again. And this time we're going to have this whole thing take 1 second. 1 second for a complete loop. So it's obviously going to be this. It's going to make that same pattern again. But now what is the period from end to end where we repeat our cycle? How long is that?
1 second.
1 second. Okay, so that's a 1 second period. So if we were to say, okay, it takes 1 second to go around one time, we could say that it takes, our frequency would be 1 second per thing that happens. Okay, so I'm gonna instead clap my hands at a rate of 1 second. All right, so if I clap my hands at a rate of 1 second, the thing that we're doing is called a clap. So that's 1 second per clap. Now this one gets a little interesting. So now I'm going to do it at twice the rate. Okay, so how long does it take per clap if I clap twice every second?
Half a second.
That's right, it's half a second, not 2 seconds, but a half a second. So that would be 0.5 seconds per clap. Okay, so the clap is a thing. Now, if we were to take this full trip around, that would be known as a cycle. Sorry, this is actually a period, not a frequency. Okay, so our period is 0.5 seconds per thing that happens. Well, okay, so obviously this is somehow related to the number of things that happen per second. If we were to take this ratio and invert this upside down, instead of time, instead of a period, we would have a thing
Frequency.
per per 0.5 seconds. And if we normalize this to 1 second, well, we would take the top and bottom and multiply them by 2, and we would get 2 things per second. Well, a something per second, that is known as a frequency, and it's measured in this thing called hertz, named after Heinrich Hertz. So basically now, if I clap like this, twice per second, we have a frequency of 2 claps per second. If I have something that is sitting on the circle and it goes around, let's say 10 times per second, it would have a frequency of 10 hertz. If we were then to, let's say, draw this, and we made it look like this, we would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like that. I would have 1, 2, 3, 4. It's really kind of ugly. 6, 7, 8, 9, 10. If we had a frequency of 10 hertz, how long would it take to make 10 patterns?
1 second.
1 second. So that's 0, and that's 1 second. This would be 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, and then 1 second. So if we were to increase this to, let's say, 100 hertz, in a period of 1 second, how many times would I have to draw that?
100 times.
Yeah, it looked like kind of like this. And that would be like 1 second. Okay, now if I were to draw, instead, if I were to move this thing around the circle 1,000 times a second, what would my graph look like? If this was 1 second.
1,000 times.
That's right. It would basically look like this. And you'd basically just see this like block, because I couldn't even draw it that close. Essentially, you'd see a constant amplitude block that filled in the whole gap, unless you could speed up the measurement. How about if I made this 1,000,000 times?
You would draw 1,000,000 things.
I draw it 1,000,000 times. So basically it just gets solider and solider and solider because you can't even see the changes. Okay, so where this is going is that, okay, we now have this thing that's going around, or it's basically generating a sine wave that's going up and down and up and down and up and down this number of times per second, because the thing is going around the circle that many times per second. Now, I could also draw this starting here at the 0 point. Now, the question that I have for you is, what exists to the left of this that I just drew? More of the same, right?
Yeah.
How about to the right?
Infinite.
Same thing, right? Okay, now, so what does that mean? Does it really matter if I start right here or right here or right here?
No.
It does not matter. Okay, now, the other thing is, what if I were to take it and say, okay, well, you know what? I'm going to just draw another one that starts right here. Does it have a start and an end? No. But this one, the black one, starts right here. And the blue one starts when the black one has already gone through half. And how many degrees are in one circle, everyone?
360.
360. So this is 360 degrees. So how much later does the blue one start if I were to measure it in degrees?
180.
180. This is known as a phase shift. And as it turns out, I could also draw something called a cosine wave, which measures how far left and right it goes versus up and down. And it turns out that it looks exactly the same, except that the graph starts right here. And how many degrees is this? If it's
90,
a quarter,
90,
that is
90.
90 degrees. So a cosine wave and a sine wave are really just the same thing shifted by 90 degrees. And congratulations, you've made it through trig. That's all the trig we're doing. All right, so now where do we go with this? We now have these waves that go up and down and up and down and up and down. And they have a period, which is its t. That's the amount of time needed to go up and down. Now, the only other thing we can say is as these things go up and down, really, if we were to draw this in distance, well, it's not really moving. It's just going up and down. So we would actually be able to draw this and say, okay, well, it goes up and it goes down and it goes up and it goes down over and over and over, but it just goes up and down. And what does that make? A vertical line. Kind of boring, right? I mean, it's just basically like if I were to hold up a flashlight and if everybody can see this, I hold up the flashlight and it just go up and down and up and down and up and down and up and down. Pretty boring, right? But now what if I take the flashlight and as I'm going up and down, I move it to one side? What does that make?
Sine
Makes
wave.
a sine wave again. Yeah, pretty cool. So it's basically a traveling sine wave. So now, obviously, since I moved the thing, that actually allows our up and down movement to carve out a picture in space, which strangely enough looks like that again. Well, now, how is that related, though, to how fast I was moving that flashlight? If I wasn't moving very fast, it would look like this. If I was moving really fast, it would look like this. Right? I couldn't even fit it all on there. If I was moving even faster, it would look like this and get stretched out even further. So if I were, let's say, doing sound waves, how fast do sound waves travel? Sound waves travel at about 300 meters per second. So I am going to take a frequency of 300 hertz. And so that means that my thing is going up and down 300 times per second. And in that same second, how far have I traveled in this direction? How many meters? 300 meters. So if it's 300 hertz, I would have to draw 300 of those up and downs in here, which obviously is not to scale because then it wouldn't fit on the page. But if that were the case, and I had 300 of these, and I had 300 waves, and the distance was 300 meters, how long would it be between each one?
1 meter.
It would be 1 meter. That is known as a wavelength. Because this thing looks like a wave, we use the Greek letter lambda for wavelength, and that basically determines, that's a representation of how much space is carved out for something to travel and make one full wave pattern. So a 300 hertz tone, which is like, and I don't know if anyone could hear that. Let me see. How about now? Okay. That tone, as it travels through space, has a wavelength of about 1 meter as it travels through air. Obviously, if it's a different medium, it carves out a greater distance or a lesser distance. Now, just to make this interesting, what we're going to do is we're going to say that we have an electromagnetic disturbance. An electromagnetic disturbance is a kind of a complex thing, But essentially what we have is an electric field and a magnetic field. And these things combine to translate to motion, which is known as the S vector, which is the pointing vector. And if anyone wants to see how this works, this is known as electromagnetics. It's an electromagnetic wave. Unlike a sound wave is a pressure wave. This is an electromagnetic wave which is caused by the movement of electrons. Our E field, this is our electric field. Our H field, it can also be the B field. This is known as our magnetic field. And one thing that's very important to note is that these are always perpendicular to each other. They're always at right angles. In addition to that, the direction of movement of the wave, the disturbance as it travels through space, is perpendicular to both of them. So obviously it requires 3 dimensions. This was one of the things that Maxwell figured out a long time ago, and then Hertz was able to extend upon. The way to do this is if everybody holds up your right hand, your thumb is the electric field, your index finger is the magnetic field, and you can't use your left hand because the left hand doesn't work. It has to be the right hand. And then the middle finger is the direction of movement. This is known as the right hand rule. E cross H is S. So as I have electric field and magnetic field, this is the direction of movement, which basically means that if I were to draw an electric field that goes like this, has that wave pattern, my magnetic field at the same time would be going like this, as the wave was traveling in that direction. So electric and magnetic fields have to coexist. This is interesting because as these waves travel through space, they may encounter other things. Electromagnetic waves, unlike sound waves, can actually travel through empty space very, very well. It's a good thing because if they didn't, we would be a dark planet. The sunlight would never get here. It does go through empty space quite nicely. Now, the other thing about electromagnetic waves is that as they travel through space, they may encounter different things, such as water, right? Is water the same as air? Is the same as a vacuum, which is nothing? The answer is no. They're all quite different. They have different indices of refraction, which are caused by how the light interacts with the waves themselves and changes the speed. This is the reason why if you take a spoon and you stick it into a glass of water, it looks like your spoon is bent. Suddenly, when you pull the spoon out, you'll notice that it's not bent. Your spoon is actually fine. This is actually caused by different indices of refraction, or more generally, how the light or the electromagnetic wave interacts with the different properties of the material, the electric and magnetic fields, how they interact with the different properties of the material, which in this case is water. It could also be a crystal like quartz. It could also be salt, like a big salt crystal. That slows things down also. Okay, so now we know that this thing is traveling, electromagnetic waves travel at 300 million meters per second, which is really fast. This is also known as the speed of light. The reason it's known as the speed of light is because, I'm going to put this on the screen. Yes, I'm going to unshare that. And here we go. Has anybody ever seen this, something that looks like this before? Okay, so notice we have all the way on the right-hand side, Roy G. Biv. Hopefully everybody recognizes this as the colors of the rainbow. Those are known as visible light. To the right of that, we have shorter and shorter wavelengths, which translate to higher and higher frequencies. That is ultraviolet. And to the right of that, we have X-rays. To the left, or longer wavelengths than red, we have infrared. And then all the way to the left of that, we have this thing called radio. And you'll notice that across the bottom, we have wavelengths that get longer and longer and longer by factors of 10. And across the top, we have frequencies that get higher and higher and higher and lower and lower and lower by factors of 10 as well. And this is a logarithmic graph, and this is typically how wavelengths are shown. When we go to look at this graph right here, this big chart, you will see that each successive line is 10 times bigger than the previous one when you actually go to look at it. So this one up top covers from 3 kilohertz, which is 3,000 hertz, up to up to 300. Then the next one goes from 300 to 3,000. Then from 300 to 3,000, which is megahertz. Then from 3 megahertz to 30 megahertz, and then 30 to 300. So each one of them, as you go down on this chart, actually has 10 times as much space as the previous one above it. And this is just the way that these things are typically shown. So that means that if we look at this one right here, which is at 30 megahertz, if this starts at 30 megahertz and goes to the right and we have 300, how much space is actually in there? 30 take away 300 is? Or sorry, 300 take away 30 is 270. But now let's look at the one right below it. All the way to the left, we start at 300 megahertz, and on the right, we go to 3 gigahertz. That's a different prefix. That's actually 3,000 megahertz. So it's 3,000 take away 300 is 2,700. And then right here, 3 gigahertz up to 30 gigahertz. This is 30,000 take away 3,000 is 27,000. That is why those frequencies are really, really popular with satellite companies and with Wi-Fi services and cell phone companies. The higher the frequencies you go, the more space there is available, and that's known as available bandwidth. So that's why you have to take that graph with a little bit of a grain of salt. Okay, last thing before we go to break. All right, so now we are moving with a wavelength. We have a wave. It's traveling to the right. We're going to draw our corresponding waves, magnetic field. And as we do this, we know that this particular wave is traveling at a ridiculous speed of how fast? Because it's an electromagnetic wave. How fast does it travel?
Light speed, 300.
Light speed, speed of light. So that's our velocity. 3 times 10 to the 8th meters per second, or 300 million meters per second. And let's say that this wave has a frequency of 300 million hertz, which is a ridiculously high number, right? Ridiculous. Well, so if we know this is true, this is in meters per second, and this is in waves per second. Seems to me that we can divide one of these by the other and actually get something useful. So this is our frequency and our wavelength, and this is also known as C, and that's in meters per second. So what would be useful to know what our wavelength is? So how about meters per wave? That would be a useful thing, right? That would be known as our wavelength. In order to do that, we would take 300 million meters per second and divide it by the frequency. And what do we get in this case for this particular frequency? What's
One.
we 300 million divided by 300 million? That would be 1 meter. So a wave, an electromagnetic wave, traveling through space at the speed of light with a frequency of 300 million meters per second, or sorry, 300 million hertz, will have a wavelength of 1 meter. In other words, it will physically carve out a distance of about 1 meter long. What if I were to take this and knock off a zero? And our frequency is now 30 million.
It's no longer at light speed.
No, it's still at light speed because it's an electromagnetic wave. You can't change the speed. What I did is I changed the frequency.
So 10 meters.
Yeah, all electromagnetic waves travel at the speed of light, unless they're in some other medium. They travel at the speed of light. So what's 300 divided by 30?
10 meters.
10 meters, or about 33 feet. Now, what if I were to take this and knock off yet another zero?
100 meters.
That would be 100 meters long. Okay, now, that would be 100 meters long. How big is 100 meters? Anyone play soccer?
It's a football field length.
Football field. That's a football field length. That's right. So this is known as, this frequency with 10 to the 6th or 6 zeros, that would be known as 3 megahertz. So what we're going to then do is say, okay, we're going to make this 1 megahertz. Okay, so now what is our new wavelength?
300 meters.
That would be 300 divided by 1 is 300 meters. How long is that? Approximately. 300 meters?
3 football
Yep,
fields.
300.
About 1,000 feet. Yeah, it's about 1,000 feet long. Okay, what operates at the frequency of about 1 megahertz in frequency? Okay, so what we're going to do is go up here. We're going to zoom in on this area, and we're going to go to about 1 megahertz. And I'm going to ask you what you see. What does that say?
Broadcasting AM radio.
AM radio. Okay, so here's where we get interesting. So we have a frequency of 1 million hertz, which is 1 megahertz. And our formula, C F lambda, we can actually write this like a circle or a triangle. We X out the one that we don't know. We don't know the wavelength. And then we're left with C divided by F. So lambda is equal to C divided by F, which is 300 million divided by 1,000,000. Cross out those zeros. Normally we just leave those off. And we end up with a wavelength of 300 meters. Okay, an antenna to generate this wavelength, or any wavelength for that matter, is typically going to be at least 1/4 of a wavelength long. So what is roughly 1/4 of 300 meters?
75 meters.
75 meters, which is about 280 feet. Now it's about 250 feet. Okay, so this is about 250 feet long. Wow. Okay. Where do you see something like that? Remembering that if you have a broadcast station, you want to broadcast to everybody. Where you would find that is typically 1 or 2 or 3 really tall radio towers in the middle of a field. Now, This is not an inexpensive thing, right? And where do you intend to listen to AM radio frequently? In your what?
In the car.
In the car. Okay, so in order to hear an AM radio station, how long should your antenna really be?
Pretty long.
Should be a full
250
car
feet.
midway.
Now, who has a 250-foot wire streaming off the back of their car as they're driving down the road? Anyone? I certainly don't. So what you typically do then is you take a coil of wire that's about 250 feet long, and you put a bar magnet through the center of it, and you connect that to the radio, and it's inside your car, and that allows you to receive AM radio. Not very well, but typically the towers that are operating nearby have enough power that you can actually still receive it fairly well. You can't transmit on it, but you can receive it pretty well. All right, here we go. The next one, FM radio. We're going to say that this is about 100 megahertz. Okay, that's 100, 0, 0, 0, 0, 0, 0, and C, F, lambda. We're going to actually start doing this. We're going to use this in megahertz, and we're going to replace C with 300. So that's our memorized circle. So we have 100 megahertz. We have our circle, 300, 100, and lambda. Which one don't we know? We don't know the lambda. Lambda is equal to 300 divided by 100 is 3 meters long. And as I said, to have an antenna that's functional, it needs to be at least a quarter wave long. And a quarter wave would be how long?
meters.
0.75 meters, which is about 2.5 feet. Now, is that a practical antenna to build?
Yes.
Yeah, you can put it on your car. That's the antenna that sits on the hood of your car. That is an FM radio antenna. Now, so when you look at the dial, however, what you'll notice is that your FM radio goes from 88 to 108. That's known as FM. Your AM goes from 530 to 1700. All right, which one's a higher frequency? Obviously, one of them has bigger numbers than the other, right?
FM.
No.
Well, what happens is that this is in kilohertz, and this is in kilohertz, and you have to know that kilo means 1,000, and this is in megahertz. And you have to know that mega means 1,000,000. So obviously FM radio is a much higher frequency than AM radio. But people don't usually bother to think about the fact that there are units after it, and that's why it doesn't look that way. All right, everybody ready for a 5-minute break?
Yep.
I need a refill on my coffee.
Good.
Think of all your questions, everyone. Come back from the break with questions.
Hello.
No, the test is not open book. But you can study all you want. And the other thing is that I will bring up now, the question pool is such that all the questions and all the answers are available. So if you take practice tests, you study, you will never get a question that you've never seen before. All right, so I want to know from the kids, does this apply to what you guys do in science class yet?
Not at all.
Not at all?
Entirely not.
So you know what? You're going to be so far ahead that when you get to this is basically like an intro to physics. You're going to be so comfortable with this that you're going to basically be able to, like, not that I would recommend doing it. You're going to be able to sleep through class and still be okay. You're going to be able to correct the teacher.
Thanks for the advice.
I don't recommend sleeping through class. Although I have to admit, when I was in college, I did. You know, I sat in the front row every single day, and I still fell asleep. So the teacher knew me as that guy who sat in the front row and fell asleep right in front of me every single day. Okay, so, all right, we had a great question. All right, is everybody ready to keep going? Did we think of more questions? See, I was not addicted to coffee at that time in my life. It says coffee saves lives. I know. I hadn't discovered coffee yet. Okay. So somebody asked, well, what actually happens when you change the frequency? Tracy, was that coffee mug just close to the camera, or was it really huge?
It's really huge.
It's really huge. Okay. Time divided by time divided by anything is not a frequency, it's a period. Something divided by time is a frequency. Like how many times per second. All right, so the question was asked, what actually changes when you change the tuning on something? Okay, so what I'm going to draw is an antenna coming down into a black box. All right, so this black box is a receiver, and we can actually say that the antenna has no real ability to discern what's coming in. It receives stuff from 530, let's say it's an AM radio, all the way up to 1700 kilohertz. And you want to listen to one particular thing, right? You don't really want to listen to everything. You want to listen to one thing. Well, so what you would do is you would intentionally inject a second frequency into this box. And what happens is that you then have this device known as a mixer, which we're actually going to get to in the next couple of days. And we're going to call this into this frequency, we're going to call this a variable frequency oscillator, which means you can vary it. And we're going to make this a very simple receiver and say that we're going to have a frequency that this can tune from 530 to 1700 kilohertz. And the way you would tune this is you would actually have an inductor, which we're going to get to probably today, maybe, and a capacitor. These are frequency sensitive components that you can vary in value, and those change the resonant frequency of an oscillator, which changes a frequency that you can actually generate. This is a very special device called a mixer. And what comes out of the mixer is sums and differences. You kids in school, what's the difference between a sum and a difference?
A sum is when you add them both together. A difference is when you subtract the.
That's right. Sum and
subtract the
difference.
lower one.
Exactly. Okay. So now let's say that I have this set for 640 kilohertz. And I have this output designed with a filter that is designed to receive and actually be able to listen to stuff from right around 0 to 1000 hertz, really low frequency. If that were the case, where would I get 0 if I'm looking at the difference? If I'm using 640, what value here is going to produce a difference of 0?
640.
640. Okay. Which means that if I were to hear, let's say 720, what would 720 minus 640 be?
80.
80. That would be way up here. What would 530, what would 640 minus 530 be? Or other way.
1000,
It could be negative,
100.
it could be 110. It's going to be either high, above, or
110.
below. This is known as a band pass filter. I'm going to receive everything that's inside that filter. And I'm going to reject everything that's outside. So what does that mean? What station am I going to hear? Just the one that I want to. And I'm going to ignore all the other stuff. So when you tune a radio, that is what you are doing. This is actually known as a direct conversion receiver. This is a really, really, really simple design, but it's the most basic one there is. Then beyond that, you can actually add additional stages of multiplication, which is known as heterodyning, to create intermediate frequencies, which are literally intermediate. And then you can build your componentry on the inside so that you have multiple stages and multiple degrees of filtering, which makes your receiver better and better and better.
So Scott,
Yeah.
Is it the mixer that is specifically changing the station, or is it the filter?
Neither.
Neither?
It's the variable frequency oscillator that you're pumping into it.
Oh, okay.
You're generating an external frequency that you pump into the mixer.
Okay, I think that makes sense.
Okay. Yeah, go ahead. I heard somebody else.
So when you say heterodyne, are they intermediate interfrequencies between that, or are we going to?
It depends how you design it. I mean, if you design a three-stage super het receiver, your block diagram might be like this. We have a filter, and then you have another IF stage with a mixer, and another filter, and another mixer stage right here with another one and another filter, and that goes into something else. So, and this one might be, let's say, 70 megahertz, and this one might be 9 megahertz, which have nothing to do with the frequencies coming in. And this one is usually 455 kilohertz. That's the down conversion, and then this goes to your audio amplifiers. And this is known as your product detector. So, I mean, yeah, depending on how you design it, and that's why RF design is one of those cool things that you can actually, you know, it's not that hard, but it allows you lots of freedom and allows you, this is a real skill. This is being able to do that, and the fact that, you know, you might have, okay, this has sums and differences, right? Well, what if the frequencies that you're listening to are here and here and here, and there happens to be another station that's really, really strong way over here, such that it is so strong that you are not expecting a difference that would be strong enough to pop up in here. But all of a sudden you get it, because the mixer, it mixes stuff. You can't control what it mixes. And that's actually known as an image. And sometimes you'll get an image of something that you didn't ever expect. And that is because you are really nearby to some other station that's generating a lot of energy. So how would you get rid of that? Well, this was unwanted in the first place. So you would add a filter to filter that out so that it disappears before it even gets into the radio.
Does that have anything to do with compression?
No, compression is something else altogether. Compression comes down to modulation, which we're also going to get to.
We used to live next to a radio tower in North Pole, and we'd hear broadcast signals through the microwave and the toaster and other things when they were on.
Even when they weren't on. I mean, even like I actually, when I was I used to live nearby to an AM radio station. It was WJOK 1150, all comedy all the time, which was great, except that it was 150,000 watts on AM, and when I lived a mile from it, and I could receive it anywhere on any frequency because there was enough energy being transmitted that I could hear it anywhere. If I drove by, I could actually listen to it on my car radio, even with the car radio turned off. I could actually hear it through the speakers. Okay. Continuing on. All right, so if everybody has the book, and what we're going to do with the book is we're going to jump around in the book a little bit, and it's the electronic version, and the pages are not numbered on the pages themselves, but they're numbered on the pages of the PDF. So,
what book?
What book? Did I hear what book?
Yes.
Okay, on that, did you get the big email that I sent you? In the big email that I sent you, there's a 10 megabyte zip file. So contained in there is the no nonsense guide. There it is, the no nonsense guide.
Several people are showing it.
Yes, they are. And it looks like, if I can bring mine up. here we go. It looks like that. This is a free book, which is, and it's actually pretty nice because it doesn't have a whole lot of detail. I figure I can fill in the detail, but what it does do is that it fairly well lays out all the questions and answers. Notice that the correct answers are highlighted. The incorrect ones are not highlighted. So in that regard, it's actually pretty helpful. This is the exact same question pool, just laid out in a logical order, as you will find online. Okay.
What page are we going to?
I'm trying to figure that one out. Okay, let's see. Radio wave characteristics. We're going to go there. So that's the 39th page in the PDF. It's called radio wave characteristics. Okay. So given the fact that we've kind of talked about this, let's see how well people remember what we talked about. The two components of a radio wave, considering a radio wave is an electromagnetic wave, are electric field and magnetic field. And radio waves that contain electromagnetic waves, the electric and magnetic fields are always going to be at right angles to each other. How fast does a radio wave travel through space? Everyone?
Speed of light.
Speed of light. And what is the speed of light approximately in meters per second?
300 million.
300 million meters per second. Really, really fast. Or about 1/7 of a second to go all the way around the world. Or to the moon and back, about 3 seconds. Or how about from the sun to the earth?
8 minutes.
About 8 minutes. Yep. So the light that you see outside was actually sent out of the sun 8 minutes ago. Okay, the formula for converting converting between frequency and wavelength. We can draw that circle, and we have the speed of light and frequency and wavelength. And see, if you ever start to get mixed up with regard to how you lay it out, we always can go back to that circle. I believe in scribbling things down. If you can generate that and just cross out the one you don't know, let's say that we measure a wavelength of 6 meters. Okay, so that means we don't know the frequency. And then we're left with 300 divided by 6. So F is equal to 300 divided by 6 is
50.
And 50 megahertz, because the unit is in megahertz. And actually, as it turns out, this is correct. 6 meter band is roughly 50 megahertz. So, and that way you don't have to memorize what is a formula for converting frequency to approximate wavelength in meters. You can always go back to what you know and write out the equation, and then you don't have to worry about it. The relationship between wavelength and frequency, it is an inverse relationship because of what we just drew out. The fact that as your frequency increases, your wavelength gets shorter and shorter and shorter. What is your frequency? Like, let's say we're looking at a red laser. A red laser has a wavelength of about 660 nanometers. Nano is a billionth. Not a billion, a billionth. So 660 nanometers, it has a frequency in the terahertz, which is very, 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 very high. That's like 1 trillion hertz. And that's the color red. So if we look at that frequency chart, and we look at this electromagnetic spectrum, we go back to this, and you notice on that spectrum, as you go higher in frequency, what happens to your color? It starts at red and then becomes?
It becomes more, travels down the color wheel.
Yep. And what's the last color before you get to ultraviolet?
Purple.
Okay, now this is really important too. There is also a relationship between frequency and energy. And this is something that Einstein worked on. The fact that as you get higher in frequency, you have higher energy photons that are carrying them. So which one, red or purple, has higher energy?
Purple.
Purple, okay. Which one has higher energy, ultraviolet or X-rays?
X-rays.
Okay, so ultraviolet and X-rays, X-rays in particular, are known as ionizing radiation. They actually have enough energy being carried along in those photons to strike an atom, transfer their energy to it, and tear an electron completely out of the atom. And if we're looking at atoms, atoms are protons and neutrons in the nucleus and electrons flying around the outside. And that is why X-rays, if you get irradiated, it can destroy your cells. Now, light, if we're just standing in red light, not so much. How about ultraviolet? What did they say ultraviolet causes?
Skin cancer.
Yeah, it causes skin cancer. The reason it causes skin cancer is that it actually causes electrons to be torn off of the atoms in your body, which can cause changes in your DNA. X-rays can as well. But now when you get down to infrared and then into radio waves and even microwaves, these are known as non-ionizing radiation because they do not carry enough energy in their photons to do bodily damage and cellular damage. They can cause heating by vibrating vibrating atoms back and forth, but they don't cause genetic damage. Okay, next, let's see. Okay, here we go. What frequency range is referred to as HF? Okay, HF is high frequency. That is 3 to 30 megahertz. And again, what does mega mean, everyone?
Million.
Mega means million. Yep. How about kilo? Thousand. And giga?
Billion.
Giga is
100 million.
billion. Nope, giga is billion.
Billion.
Okay, so HF is the high frequency band, and it is 3 to 30 megahertz. VHF is very high frequency, and it is 30 to 300. UHF is ultra high frequency, and it is 300 to 3000 megahertz. And those are really important to memorize, just to memorize them. And RF is known as radio frequency. Okay, so now we're into propagation. So we're going to cover propagation. And eventually we're going to get back to Ohm's law, but we're going to do propagation now. Propagation is how things travel. So let's say that I have something that is a wave that is traveling. By and large, what do light waves do when you send them off? They travel in a what?
Straight line.
Straight line, yeah. They can sometimes diffract if you give them a slit, and sometimes they can go this way and this way and this way and cause an interference pattern, although that's an advanced physics thing and we're not going to get into that. For the most part, light travels in straight lines. Now, what happens is if something is going to bend light, what it ends up doing is it creates a better path for the light to follow. And that's why, again, you might have a situation where if you're looking into a glass full of water, you have a spoon that looks like this. It looks like it's bent. And that's because the light, it's still traveling in straight lines, except that the straight lines are being slowed down. So it looks like it's actually bending. But as far as the light's concerned, it's still going in straight lines. Now, one additional thing is that, let's say you have the Earth, which is curved, and you transmit a radio wave. To a certain degree, the radio wave will tend to follow the curvature of the Earth a little bit. Light wave will travel in a straight line. So which one will travel further along the surface of the Earth before you can't hear it anymore?
Radio.
That's right. right here. So this is your radio wave, and this is your light wave. And this is actually known as line of sight. And the maximum distance at which you can hear something is known as the horizon. So a radio wave follows something called the radio horizon. And the radio horizon is typically a little bit further than the horizon, which is what you can see. Radio waves tend to hug the surface of the Earth a little bit longer. The lower the wavelength, the more they follow. So a really long wave might do this. And the horizon would be way out here. Okay. Let's see.
Can I ask one quick question?
Yes, please.
Is that because of the fact that they're electrical and the magnetic surface of the Earth? Is that what causes it to follow the Earth instead of like a light does?
No, it's actually atmospheric refraction.
Okay.
So basically the atmosphere, if you want to think of it this way, and actually it's kind of good to do this. So here's the surface of the Earth, and we are surrounded by, if we were just transmitting on a rocky planet with no atmosphere at all, everything would just go in straight lines. But we're actually in this kind of a cloudy mess, which is our atmosphere. And as you go higher and higher, the atmosphere gets thinner and thinner, and it goes up to about 600 miles. So, but the density is really high down at the bottom, which is fortunate because that's the air that we breathe. And radio waves that travel through here tend to be bent slightly because unlike space, which has, space is space, it's empty, light waves travel or actually because space is basically empty, and this area is actually full of oxygen and nitrogen and water vapor and carbon dioxide and things like that. And it also has inversion layers, which you might have a little bit of high temperature, low temperature, which causes a different index of refraction. What you'll end up with is the fact that at radio waves, you'll end up with a certain amount of bending of those waves as they travel. And UHF signals are rarely heard beyond the radio horizon because UHF signals behave as they're aimed toward the sky, kind of like light. When they hit the upper levels of the atmosphere, they typically just pass right on through. Now, this makes them very useful for talking to what, do you think?
ISS.
Yeah, satellites. Because the waves typically pass right through the atmosphere as if it's not even there. If you point it straight up, it's like the atmosphere is clear. Now, if you were to take that signal and aim a slightly different signal at a different frequency, like this, and let's take VHF instead and aim it up toward the sky. Sometimes they'll pass right on through, but sometimes you'll get a layer in the atmosphere that tends to catch and bend light waves back down to Earth. And this is refraction. And if this right here is the horizon, the radio horizon, what do you notice about where that wave is coming through?
Further.
It's much further. This is actually known as a form of skip because we're skipping over a certain area and our bounce or our bend, which occurs up here, allows our signal to come back down somewhere far away. Now, we can also, using this same method, if we're lucky, have a temperature inversion that might exist up here, which causes different indices of refraction. And so we might have, typically as you get higher in altitude, what happens to your temperature?
Lowers.
Goes lower. When you're flying in an airplane, the next time you're flying in an airplane, it's about minus 80 degrees Fahrenheit up there. Pretty cold. That's why, you know, airplanes are heated on the inside. And you typically lose about 3 degrees per 1,000 feet of altitude. Well, you can actually get this thing called an inversion at altitude, where your temperature goes down and down and down, but then in this layer it goes up, oddly. And that changes the density of the air, which also changes the index of refraction. And so your radio signal, which might go up, well, it can actually get refracted back, but then it hits another layer and goes like this. And what does that look like? What would let's hear a name for that? What would somebody call that?
Sine wave.
Yeah. What's another name?
Ducting.
That would be a duct. Yeah, a duct. Think of like a tube, right? This is actually known as a duct. Or one might also say this is in microwaves, this is like a waveguide, where it actually traps the waves inside and eventually lets them out somewhere. And by the time it gets down to here, it could be 1,000 miles away as opposed to just a few miles away. And this typically happens at VHF, and that's known as ducting. All right, another one that is really interesting is, okay, has anybody ever had experience with a handheld radio? If so, raise your hand. Okay. Have you ever noticed that you could be standing somewhere and somebody does not have a particularly strong signal, and then you move a couple of feet over to one side and they get nice and strong? Yeah. And then you move a little further and they disappear again? Why is that?
Is that from the sound waves bouncing off the off buildings and so on and so forth?
Well, when you said sound waves, no, it's not sound
radio
waves.
Radio waves. I'm sorry.
It could be bouncing off of any number of things. Okay,
right.
So what we're going to draw is point A and point B, and we're going to say that we are operating on a frequency of on a frequency of 300 megahertz, which has a wavelength of 1 meter. We're going to make this easy. 300 megahertz is not a ham band, but it's very convenient because it has a wavelength of 1 meter. So if I draw a wave right here, how long is that wave?
1 meter.
1 meter long. Okay. If this is a distance of 1,000 meters, how many waves are there going to be in between the two of us?
1,000.
1,000 of them. That's right. There's going to be 1,000 wavelengths. So this pattern will be repeated 1,000 times. Okay, now what we're going to do is draw an alternate pattern, right? Now we said that radio waves, like light waves, like to travel in what? How do they like to travel?
Straight line.
Straight lines, okay. Well, are you also, let's say you're transmitting, are you not putting out a signal that goes off in this direction? Yeah, probably. And this one, and this one, and this one, and this one, and this one. You're probably putting off radio waves that travel in a whole bunch of different directions, whether you like it or not. The most useful one is the one that's going this way, right? What if there is, let's say, a rock that is right here? And the rock is placed and is reflective just so a signal that goes in this direction will travel like this and bounce off the rock and get to point B. All right, which one are you going to hear, everybody?
The straight one?
No, I don't think so. You're going to hear the straight one. What else are you going to hear?
You're going to hear the other one also, which is bouncing off and coming there.
You're going to hear the other one. That's right. So you're going to hear both. This is known as multipath. Now, multipath is unavoidable because can you control where that rock is? Not really. There's a rock, right? It's a rock. Somebody put it there. or it's been there for 1,000,000 years. You can't really control that. Let's say that this path that is being followed is 1,000.5 wavelengths. Okay. What is the difference in path length between 1,000.5 and 1,000?
0.5.
0.5 wavelengths. Okay. So now what we're going to do is we're going to draw our graph. Just like that. Okay. What is this thing right here called? A wavelength. How much, by the time it gets to the end point, how delayed is that green wave?
Just slightly.
How many waves delayed is it?
Half.
That's a half of a wave. Well, where's a half of a wave on this thing? It starts right there. And so it's delayed a half a wave. So it goes like this. Does anybody see a problem with this?
Do they cancel each other?
What happens if you add them together?
Phase shift.
Yeah, what happens if you add those two things together?
You get phase shift.
If they're exactly equal, all your pluses add
No,
to
it's
your
just
minuses.
you get destructive interference, so
get
you wouldn't hear any.
destructive interference, and they completely cancel. Now, it might not be that the green one is quite the same amplitude as the black one, because it did have to go through a rock, but let's say that what happens is that it tends to counteract what you're trying to listen to. So what would be a proper response to this? What would you do in order to fix this problem?
Move.
You would move. That's right. Simply put, what you would do is you can't really control that, but let's say you move a little bit this way. And your new location is right here. And now that wave travels 1,001 meters. And your black wave, it still travels 1,000 meters to get there. And what happens if you draw them out now? You have this one, and this one arrives one full wave later. And now what happens? Those waves are known as in phase. And what do they do at that point?
Amplify.
They add together instead of cancel each other out. So by moving, let's say a half a meter to one side or the other, all of a sudden, a half a meter is only this big. By moving your antenna just that far, you can actually go from an area where you're canceling signal to building signal instead. Now, if you're in a car and you're going this way, what you might hear is the fact that you pass through those areas very, very quickly. And that generates a rapid flutter, which is known as picket fencing. Because it sounds like you're trying to talk to somebody through a picket fence, where you're basically, you have all these pickets, all these, pieces of wood that are blocking your sound. Okay. That's again known as multipath, and we're talking about picket fencing. Okay, so we are on, just out of curiosity, in case anyone's curious, page 43. If we were using data transmissions and you have multipath propagation, the same way that your signals are going to do this if you're trying to talk to somebody, if you're trying to use data, computers talking to each other, what'll happen is that your data rates are going to go down and your error rate will typically go up. So basically your signal is not going to be as solid as it should be. Now, you can also use this to your benefit, believe it or not. Let's say, go ahead.
Page 43, is that the numbers on the?
I don't have it numbered on mine. It looks like this.
If you're looking for it on the PDF, on the thing that he sent out, it's page 38.
Oh,
thank you.
Is propagation modes.
Yep, thank you. Okay, knowing how VHF and UHF signals propagate can help you communicate even in adverse conditions. So let us say that we have we're in a location where we're trying to talk to somebody else, and there's a big metallized glass building. It looks like a big mirror. And it is in the opposite direction between us and the person we're trying to talk to. Well, if you have a directional antenna, you might actually be able to point it in that direction and intentionally bounce signals off of the thing that you're talking to, off of the thing that's in the wrong direction. One of my friends here, who's he does a lot of off-roading and camping and backwoods stuff. He was up around Mount Hood, and he managed to talk to some people down here in Eugene by bouncing signals off of Mount Hood. He aimed his antenna right at Mount Hood and talked to people in Eugene. So he was pointed north and pointed off of an 11,000 foot mountain and talked to people back home. So that's intentionally using a large thing to bounce signals. Which of the following can allow radio signals to travel beyond obstructions? That's known as knife edge diffraction. That's actually a single or double slit experiment for those of you who are in high school and college physics. Basically, if you take a radio wave and you hit a sharp object with it, it will tend to diffract. This is actually known as the wave particle duality, where light waves are actually photons, but sometimes they're probability waves, and some of the signal will go off in all kinds of different directions that you don't expect. That's why radio waves actually bend around sharp objects, like mountaintops. And let me ask this question. Given the fact that if you are, let's say, using microwaves at 2.4 gigahertz, knowing what you know about microwave ovens and what we've talked about, 2.4 gigahertz is a ham radio band. You aim a microwave dish, which you're using to communicate long-distance Wi-Fi with somebody, and you have a nice solid signal, and then it starts raining. What will happen to your signals?
Well, that's water in the air, so it's going to cause some vibration in the water.
And what will happen to your signal?
Weaker.
That's right. Your signal will get weaker and potentially even disappear because all that energy is being absorbed by the water. So vegetation is another thing. What does vegetation have in it? Vegetation being leaves.
Water.
Water. What happens if you try to shoot microwave energy through water?
Vibrates faster. Gets hot.
And that's right. And your signal will disappear. Interestingly, there's a museum in town that we work with called the Eugene Science Center. And for a while, they had a microwave link for all their Wi-Fi. And the microwave tower they were talking to was on a nearby hilltop. And in order to get it to work, they had to hire somebody to go up and cut a hole in the trees, cut down a bunch of branches so they could shoot their microwave signal right through the hole in the tree, right through the hole in the trees to the microwave tower. Because without the hole there, they couldn't actually use it. The signal would get absorbed. Okay, now we're on to polarization. Antenna polarization. Okay, so what are the two parts of an electromagnetic wave again, everybody?
Electric and magnetic.
Electric and magnetic, yep. Okay. And magnetic. Those make electromagnetic waves. The direction of the electric field determines the polarization of an antenna. Now, has anybody ever worn a pair of polarizing sunglasses while they were driving? Okay, why do you wear polarizing sunglasses?
Dim the light.
Typically for what reason?
Glare.
Glare, that's right. Okay. Really good if you're skiing, really good if you're driving a car. Okay, so electric field, let's say, goes like this. That would be parallel to the ground. That would be known as horizontal. This is a horizontally polarized signal. How about if it was going up and down? What do you think it would be called?
Non-polarizing.
That would be vertically polarized. Okay. Typically, the direction of polarization follows the orientation of the wire. It's not always, but usually is. So a wire that is parallel to the ground is typically horizontally polarized. It has electrons flying back and forth inside it. It generates an electric field that goes left and right. A wire that is vertically oriented would be known as vertically polarized. The electrons would go up and down, and it would generate a signal that is oscillating in the vertical direction. Okay, why is this important? Because we're going to get back to our polarizing sunglasses. Let us say that we have light that is going in this direction with the electric field. What would that polarization be known as, everybody?
Vertical.
Vertical. How about if I have a filter on my glasses that only allows light that is going this way to pass through? How much of that light will pass through that filter?
None.
None. So if I have, let's say, light that is reflecting off the hood of my car that is, really, really bright, and the hood of my car is actually polarizing it in one direction, and I have a filter that is opposite polarization from that, how much of the glare will I get from the hood of my car? Or from the sun, or from like the sunlight up in the mountains, bouncing off of the snow? Zero. And that's why these are glare blocking. Now, so this is a practical application for polarization. Now, we also have another practical application for polarization, which is if I have an antenna that's sitting on the hood of my car that looks like this has polarization that's vertical. What if I tried to listen to this signal using an antenna that was horizontally polarized? What would I hear?
Nothing.
Virtually nothing. That's right. Now, looking at this from above, there's a certain advantage to this, which is if I have this vertical antenna, which I'm now looking at from above, does any direction look any different from any other direction?
No.
Not really, which means I get signal going this way and 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 this way. And this is known as an omnidirectional signal. Now, the benefit to being omnidirectional is if a person's over here that you're trying to talk to, another person could be here or here or here. You don't have to turn your car in order to make sure that somebody can hear you, which can be very inconvenient. The other thing that we do is on top of a building or on top of a mountain, this is again from up above, we have a single dot, which is an antenna, which is also omnidirectional and vertically polarized. Does this have any preferential direction at all?
No.
No, which means that if this is our repeater station, that means that there can be people over here or here or here, all who are driving or walking around or something like that, and it does not really matter where they are, they're going to be received equally well. And that is why vertical polarization can be really useful. Now, there are certain times that vertical polarization doesn't really get used very well, and that is if we want to go really long distances and we want to use the flatness of the Earth to reflect our signals. So if this is the Earth, we would actually have an antenna that is shaped like this, for instance, that is horizontally polarized so that the waves go like this, and when they hit the Earth, they would skip back off. And this is typically known as weak signal propagation modes. So if you're trying to use signals that bounce off the Earth, that would typically be single sideband or CW, which is Morse code, or digital signals, for instance. And you're trying to cover long distances, you would typically use horizontally polarized antennas. Vertically polarized antennas, these are usually used for local FM for VHF and UHF. And does anybody remember what are the frequencies for VHF? How many megahertz? I'm going to ask you this over and over.
3,300.
30 to 300.
And then
UHF?
3,000.
300 to 3,000. Yep. Okay, very good. Okay. Let's see. Okay, so now there's a couple of distractors that I'd like to point out in one of these questions. So we're on page 45. We're still in antenna polarization. Notice that we have right-hand circular and left-hand circular. That sounds like a joke, right? Believe it or not, that's actually how we communicate with satellites. That the polarization actually goes around in a circle, like it makes a spiral in space. And it can either be going this way or this way, depending on how you build the antenna. And that's known as circular polarization. Okay, now we're talking about frequency bands. Okay, so frequency bands. Now, notice that these are called, for instance, 10 meters, 6 meters, and 2 meters. They're given in wavelengths. Now, so why do we do wavelengths? Because wavelengths give us a general idea of how long a wave is, how long, how big an antenna is going to be, et cetera, et cetera. They translate to certain frequencies. So if we were to use our math again, and we have the 10 meter band. So what's that formula? How do I draw that circle? 300. Somebody walk me through it.
Over frequency and
F and
Just C.
wavelength, lambda.
Yeah.
Okay. And again, this is megahertz. Okay, so if somebody gave me 10 meters, which one of these do we not know? 10 meters is a wavelength, so we don't know the frequency. So we're going to cross it out and say frequency is equal to 300 divided by 10, which is 30 megahertz. Now, that is not an amateur radio band. However, what we do have available to us is we have our frequency chart, which I have somewhere here. There we go. And we go to the band known as 10 meters. And what are our frequency limits?
30.
28. No, on this chart, 28 to 29.7. So they are. So the bands, the frequency bands in meters give us approximate frequency ranges, but we have to go back and know what those frequencies are based on our license class and given our license privileges. So another one was the 6 meter band. So we're going to do the math again because that's what we're here for. And we're going to draw the thing again, 300 F lambda. The answer is legality. Those frequencies are given to us to use by basically now by our license and the FCC, and the FCC working with the International Telecommunications Union. Okay, so we're looking at the 6 meter band. Somebody
50.
tell me.
50 megahertz.
Yep, 300. And F and 6. Cross that out. F is equal to 300 divided by 6, which is 50 megahertz. Okay, so now we're going to go back to our frequency chart. We're going to look at the 6 meter band. And there's a 6 meter band. And what does it cover? 50 up to
54.
54. So we actually have 4 megahertz of bandwidth up there. And actually, as it turns out, from 54 up to 60 is channel 2. So people who used to, like TV channel 2, so people who used to operate on 6 meters, if there was a channel 2 in their town, they would typically have to install filters to avoid wiping out TV signals. With cable, that doesn't happen anymore. Okay, so now the other question was the 2-meter band. Okay, we're going to do the math again. Notice that there's a theme here, which is that we're going to do it over and over and over. F and lambda. And now we have the 2-meter band. 2 meters is a wavelength.
150
is 300 divided by 2 is 1.5 meters, or 150 megahertz. Okay. Well, I can tell you that that is not an amateur band, 150 megahertz. That is something else, but we can also look at the 2-meter band and see that 2 meters is 144 to 148. And again, memorization to know that it's an approximate wavelength. And in fact, this 146 megahertz is about 2.05 meters. So it's pretty close. We call that 2 meters. Okay, so now, once we have that, I'm going to switch back to here and see that the 10-meter band and the 6-meter band and the 2-meter band use something called occasionally sporadic E. We are all very excited about this when it happens. Now, the question is, why do they call this sporadic E for long-distance propagation on normally 10, 6, and 2 meters, and 2 meters being VHF is typically going to be line of sight? Okay. 6 meters is usually line of sight, but sometimes not because of this thing called sporadic E. Well, why are we calling it sporadic E? To get into that, we need to start going back to a map of our Earth, and then we need to start drawing the atmosphere. And then we need to put the sun up here. So, above the Earth, we have the troposphere, which is where we live. And then we have the stratosphere, which is where we fly, jet planes and things like that. And these go up to about, 20 miles or so. Pretty low in atmosphere. Pretty low in altitude because their atmosphere goes all the way up to 600 miles or so. Well, at some point above this, we transition to the ionosphere. And the ionosphere is so named because our atmosphere is largely oxygen and nitrogen, and these form in the shape of diatomic molecules. Those are O2 and N2, which are flying around in space. As you go up, the density gets lower and lower, and so we have a lower and lower density of largely oxygen and nitrogen molecules that make up about 99% of our atmosphere. These actually form into kind of distinct layers with certain different characteristics. These are known as the D layer and the E layer and the F1 and the F2 layers. And what ends up happening at these layers is that the density of ionized oxygen and nitrogen molecules tends to kind of follow a certain pattern. The D layer, what happens is that because the sun is putting out all kinds of radiation, it's putting out radio, believe it or not. The sun makes a lot of radio energy, puts out a lot of infrared. That's good because we feel it as heat. It puts out a lot of light. It puts out a lot of ultraviolet. It puts out a lot of X-rays, which, if we didn't have an atmosphere, would lead to our very quick and painful death. So, good thing that we have an atmosphere. Otherwise, we would end up like Mercury, and our planet would be completely devoid of life. Well, nice thing about this is that we have all these diatomic molecules up here, and as we get lower, there are more of them, and there's even more. So by the time our radiation from the sun gets through this layer, maybe this picks off a few UVs and X-rays, and by the time it gets to here, it picks off a few more, and by the time it gets here, it picks off a few more, and when it gets down to here, basically almost nothing gets through above a certain, above a certain point. So you get really, really high densities of ionization down here. And a little bit lower in the E layer, and a little lower than that in the F1, and much lower in the F2. Well, as it turns out, when you send radio waves up into these layers, what happens is that the D layer tends to absorb up to 10 megahertz. But now the D layer, because there are so many, and I should cover exactly what ionization is. When something ionizes, there's enough energy to pop an electron out and make a plus and a minus charge. So when you end up with those clouds of pluses and minuses, you essentially end up with a plasma where you have more electric charges floating around. And what are electromagnetic waves? What's a big part of electromagnetic waves? Is that electric part. So at certain frequencies, what happens is that there's just so much ionization up there that energy that gets there either passes through or gets absorbed. So anything below 10 megahertz, when it hits the D layer, just disappears. Now, as you might expect, when there's the middle of the day, you get a lot of ionization, but as soon as night comes, you have no more ionization coming out of you have no more energy coming out of the sun on the night side, and you have a lot of opportunity for recombination of those pluses and minuses that form. So the D layer forms during the daytime and then disappears at night. When you get up here to the E layer, it's a little less pronounced. The F layer is a little less pronounced, and the F2 layer is even less pronounced. And what happens is that at certain frequencies, you can actually generate a region of high intensity, high density ionization in the E layer, and this is what will actually take E layer energy, like 2 meters, 6 meters, and 10 meters, and give you this thing known as E-skip, or sporadic E. Other frequencies just pass right through. Then above that, and higher in altitude, in the F layer, depending on the density of the ion clouds up here, the higher the level, the higher the frequency will typically be affected, and you get waves that go up this way and then bend back down. And what do you notice about where they're coming back down?
Further away.
They're further and further away. That's right. So the higher the level where those bounces occur, the further the distance that gets covered. And depending on also the angle at which it happens, it might be that this is a shallow enough angle that by the time it gets here, it'll just be absorbed. What would happen if we shot it straight up is that it would just pass right on through and you'd never see it again. So there's kind of a sweet spot where a signal gets bounced back down. And there's also a frequency that is dependent upon the level of ionization that causes that to happen. This is typically at high frequencies. And what is the range of high frequency again? How many megahertz?
3 to 30.
3 to 30 megahertz. And that changes with the level of ionization that occurs. So when do you think the level of ionizing radiation coming out of the sun would be at its peak on the Earth? It would be the sun directly overhead. What would that be called?
Noon.
That would be noon. That's right. And when would it start to go away? Afternoon. And then what happens when the sun disappears? What do we call that?
Evening.
Yeah, we call that night. That's right. So what happens is it changes from day to night. And because the Earth is tilted on its axis, it actually changes from season to season. So you get more pronounced peaks during the summer and less pronounced peaks during the winter. And on top of that, the sun goes through 11-year cycles where it puts out more and less ionizing energy, which means that you basically have you're basically on a daily curve and then an annual curve and then an 11-year curve on top of that. So what it really means is that it follows a general rule, but it's actually a pretty complex process. And when this gets interesting is that we can now look at, for instance, this site right here. Hopefully this comes up, PSK Reporter. And this is known as propagation, which is how radio waves travel. And hopefully this comes up. Come on, come on, come on. Notice this map of the Earth. And what are those light and dark areas called? What do we call the light and dark areas on the planet?
Day and night.
Day and night. Okay. So notice that we are in the middle of the day in Oregon. And what do we have? Where are a lot of these stripes going to? And notice they're always following a curve because the shortest path between where Oregon and Europe is over the pole. Notice that over the pole, it's basically almost light all the time now because it's getting to be spring. And what do we have? We have lots and lots of useful paths between us and Europe. How about between us and Asia? Not so many, right? So why do you think? Why is that the case? Betty, I saw you unmute yourself. Why is that the case?
It's over water.
Actually, the water is not. The water actually should make it better.
It's not daytime yet. They'll get there in a few hours.
That's right. It's not daytime yet because those areas haven't been bathed in sunlight yet. So let's look at another place. And all of these reports, by the way, are generated automatically by stations that are receiving signals and tied into the internet. So all the signals that you're seeing are reports that have been generated automatically by sending information to this server on the internet. And this is just one of those things that is incredibly cool and allows us to see what the sun is doing to us. And here we go. All right, so we're looking at Australia. Notice, what do we have between Australia and the West Coast or the Americas as a whole?
Basically nothing.
Virtually nothing, and that's because it's not even morning there yet. However, what do they have between there and Europe? Because it was recently daytime there, so those areas are still activated. They haven't faded out yet, and now you still have propagation paths between Australia and Europe. And notice that what's in between Australia and Europe as you go north-south? Australia is in the southern hemisphere and Europe is in the northern hemisphere. So what's right in the middle of it?
Equator.
You get the equator. And because we're at that time of year, the equator gets the strongest sun. So those paths that go over the equator, for instance, Australia to Africa, not so good. Australia to Europe, it passes right over, let's say, right here in the Middle East, which has gotten a lot of sun recently. So those areas have a lot of ionization still left over. So you like atmospheric physics? You like space physics? This is cool stuff. That's one of the many things that we can do with this. Okay, let's see. So basically we can bounce signals off of anything that is electric. We just actually, does anyone live in an area where they could actually see the aurora this past week?
Yes.
You guys in Alaska?
Oh yeah.
Okay. Tell me about what the aurora looked like differently this week compared to previous weeks.
Well, a lot of red, what we call high intensity colors.
Mm-hmm. Do you know why that happened?
The KP was up to 7, which was, I guess the ionization energy from the sun was at a maximum.
Yeah, we had a ton of solar radiation coming down as particles. We had and in addition to that, the sun also released what would what could only be described as a big shock wave that hit the Earth's geomagnetic shield, essentially, and basically shook the heck out of it, and then opened it up so that all those particles could come down over the pole. And so, who was it in Pennsylvania? Did you get to see an aurora? Did you get? Was the weather clear enough to see the aurora? Or New Jersey? Did you guys see an aurora this past Thursday?
We did in Michigan.
Did you in Michigan? That's pretty far south for the aurora.
It was
Yeah.
very pale.
Yeah. Well, I have been driving on Interstate 95 from Maryland to Pennsylvania and over the Tidings Bridge. I could actually see the aurora back in about 1991. And it was a big storm, big geomagnetic storm. And I thought there was something wrong. I figured, oh, that's really weird. And yeah, so basically what you're seeing is the effect of the sun on the Earth when those auroras happen. Now, because an aurora is basically a giant electric storm, you can actually bounce signals into and out of the aurora. So for you guys up in Alaska, you might have the opportunity to do auroral backscatter, which is very, very interesting and very cool. And it sounds very, very strange. So auroral signals, if you listen if you go look for them on the web, you can actually find some like on YouTube. And it basically sounds like this. Because the signals that are coming back are so they go through so many paths that voice basically sounds this bizarre ghostly sound. But you can bounce signals off the aurora. Similarly, on the 6-meter band, if you aim signals upward during a meteor shower, you can send very, very high speed data. And whenever there's a meteor trail that exists, when a meteor burns up in the sky, the reason you can see it is that it gets really hot and generates a plasma. A plasma is a cloud of electric intensity, ions basically, electrons. So long as that exists, you can bounce a signal off and actually bounce signals off of the meteor trail. Again, there's something called tropoducting, which allows VHF and UHF signals to go over 300 miles or so. And those are caused by temperature inversions. Now, if you happen to live in Southern California or Hawaii and you like hiking, there's a good opportunity for you to go up to a mountaintop and every summer work the Hawaii to California duct that forms over the Pacific Ocean, where you can take a modestly sized VHF radio and antenna, aim it toward the other place, and talk to other people who are up on top of the mountain on the other side using the duct. Again, at microwave frequencies, precipitation is rain. Rain absorbs microwave energy because it's water. And by and large, radio waves other than that are not affected by rain. So on the 10-meter band, on the 6-meter band, there's essentially no impact. So now we're going to talk about high frequency. Okay, so we did a little bit already with the ionosphere. The ionosphere is a cloud of ions that form up in the atmosphere up to about 600 miles up. Because we aim signals off of the highest layers, which are 600 miles up, those allow us to get long skip distances. And long distance propagation is very common on HF, whereas it's very uncommon on VHF. Okay, during the sunspot cycle, when we're at the top, right now we are not at the top, but we're going up to the top. 6 meters and 10 meters. 6 meters again is 50 megahertz, and 10 meters would be close to 30 megahertz. The higher the degree of radiation coming out of the sun, the higher the frequency we can use. So this past weekend, there was a contest on the air, and I am going to take this time to bring this up. A contest is basically a big party on the air where different people all over the world do their best to get on the air and just basically put out their biggest antennas and strongest signals and see how many people they can talk to in other places. So what I'm going to do is, assuming this works, okay, there we go. Can everybody see that? Everybody see okay?
Yes.
Okay, so this is operating at a power of 5 watts using voice, yeah, and just a wire antenna this past weekend from my house. So this is, again, 5 watts, and notice the band, 10 meters, 15, 15, 10, 10, 15. Conditions have been very good because the sun has been very, very active. So from my house to Uruguay, for instance, that's about 6,000 miles using 5 watts of power, which is a little bit more energy than my flashlight on my phone puts out. So imagine aiming that up at the sky and it coming down 6,000 miles away. From Oregon to China on that same band. Oregon to Cuba, that's about 4,000 miles. Oregon to Australia, that's about 8,000 miles. So clearly, this is not line of sight, because the Earth is 24,000 miles around. So that's a third of the way around the Earth, just bouncing it off the sky and off the ground. Let's see. Other ones. All of these are different countries, by the way. There's Barbados and Australia, Anguilla, Finland, and so on and so forth. So, interestingly, 2 years ago, even last year, that would have been completely impossible to do. And why is that? What do you think? Why would that be impossible?
Weather issue?
Nope. Weather has nothing to do with it.
Low solar activity.
Low solar activity. The cycle is 11 years long, and we've been waiting for 7 years for it to get good again, where those kind of numbers could actually happen. So, Betty, how old are you? Well, I couldn't hear you.
She said that she was 11.
Betty, you're 11? Okay, so the solar cycle is 11 years long. When I was licensed in 1986, the peak was in 1991 when I was 22 years old. The next one was when I was 33. The next one when I was 44. And the next one is about a year from now when I'm going to be 55. So these are long cycles. The ham radio is one of those hobbies that if you just happen to jump in and just try it for a couple of weeks, you're not going to catch the long game. The solar cycle is very, very long.
Were we looking at your log?
That was my log. Yeah. That was my log from this weekend. And notice this does say up at the right-hand side, my total count is 33,000 contacts over the last 38 years. That's not inclusive. That's not completely complete. It's probably closer to 60,000 or so.
How do you keep track of all those? Is there a special program you get for that on your computer?
Yeah, you can do it on paper. I mean, I've done it on paper for years, and I use computer logging now as well. For something like that, when there's when you're gonna make 170 contacts in a day, all over the world, and you want to make sure you don't duplicate anything, it really helps to run some computer software. And the nice thing about it is that because ham radio is it's a hobby that's really, really enjoyed by a lot of people with a lot of different skills. There are a lot of free things that people will do and put out there. Like, software for logging that has been designed and improved and improved and improved and improved 1,000 times over the last 10 years. Like the software that we use for logging that stuff is basically professional grade software because it was, designed and built and maintained and made better by people who really know what they're doing. And there's a lot of people in a lot of areas of this hobby who are, equally passionate about everything. You want to get into something and you can do it yourself, or somebody has already probably done a really good job already as well. Okay, let's see. Other stuff. So that's some propagational stuff. So that's why we have 10 meters from dawn to shortly after sunset. There we go. We're 5 years ago when I was teaching this class, we would have to say we haven't seen stuff like that in 5 years. Now I can say it happened yesterday and it's happening today. A likely cause of irregular fading of signals propagated by the ionosphere. Random combining of signals arriving via different paths. When signals get up into space in particular, let's say they go up over the North Pole and there's an aurora happening, what you get is you get a lot of different paths that signals can follow. The ionosphere is not like a smooth mirror. It's actually really bumpy and it changes height from place to place and from time to time. And you might have 8 different paths that bounce signals down to you at the same time. And sometimes they add and sometimes they subtract with each other. And sometimes they go from adding to subtracting every 10 seconds. And you'll be listening to somebody and they start to come back really strong and then for a few minutes and then they come back again. So it continually changes. Now, if you're using a handheld radio, how do you fix that? You move over. But what happens if your antenna is, like in my case, 132 feet long and is between 2 trees that are up on your property? How do you move your antenna a half a wavelength and then move it back?
Move the trees.
Well, or you just wait for it to change. So
Chop
really,
the
you just
trees down.
Yeah, well, that wouldn't serve me any good, I mean, the problem is that anything that you have, you're basically at the whim of not moving your antenna back and forth. You're at the whim of the ionosphere changing. Similarly, when signals go up into the atmosphere and they come back down, they could be either vertical or horizontally polarized, and you can't really control it. What's nice about that is that usually it's a combination of all of the above. So if you're bouncing signals up off the sky and back down, what's going to happen is that you're going to be able to use either kind of antenna, either horizontal or vertical.
What if you use a 5-element beam that you can rotate?
If you've got the money and the tower to put up there, I say do it. But yeah, let's just say that if I were to do that, I would have a much more potent signal than I do. That instead of 170 contacts yesterday, it probably would have been more like 1,500 different contacts yesterday. But I don't have that, and I don't desire to maintain a tower, and I don't desire to spend the money on permitting and everything. And maybe if I win the lottery and I buy a piece of property somewhere and I turn that into a portable, into a station, then yes. But
the
not
newer
until
technology,
that time.
the newer technology with the portable beams that you can fold up like in.
That's true.
Umbrella.
That's true. So actually, let me show that. There's something called a hex beam, and okay. All right. So this is a classic Yagi antenna, which is a multi-element antenna. Let's look up a TH6DXX antenna. Okay, let's look at high gain TH6DXX. This is when people think of a classic antenna, multi-element, multi-beam, multi-element, multi-band, high gain antenna, it's going to look something like that, right? Up on a big tower. I don't have the money or the desire to put up a big tower like that, nor put up an antenna like that. Just too much effort. However, you can do something like this. There's a hex beam. Now, what's funny about this hex beam is, can everybody see that picture? What does that look like? Does it look like a clothesline or a...
It looks like an inside-out umbrella.
Yes, it looks like an inside-out umbrella. And this is actually a different design of antenna. And I don't know if you can see, but you see the individual wires? You see the wires that are connecting those spikes together? The spikes are not the antenna. All those wires are the antenna. The spikes are basically just holding those wires out. So this is a different design of antenna. It weighs a lot less, and you can actually get some of these. There's something called a buddy hex. Let's see. Let me see. Buddy hex. And notice what that is supported by. Can everybody see that picture? What is that? What is that mounted on? Can everyone see it?
Just a tripod. Looks
That's
like
just
me.
a tripod. Yeah. So this is a portable beam antenna, and each of those, the wires up here at the top, what those are doing is those are actually a multi-element directional antenna, and the whole thing fits into a carrying bag. So again, why did people come up with this stuff? Because they wanted to. They wanted to be able to play out in the field and not have to carry an antenna system that weighed 150 pounds with them. So somebody came up with the idea of how to build one that weighed 20 pounds that they could carry around. And then when they get there, they could put it up.
We haven't gotten into antennas much yet, but will that cover every frequency, or do you need to get a bigger one, or what?
That covers the 20, 17, 15, 12, 10, and 6 meters. So if we look at the chart, let's see. That antenna covers 6 meters, 10 meters, 12 meters, 15, 17, and 20. All in one portable one carryable antenna that you can field deploy. Because somebody said, let's build one of those. Let's design it and build it. So that fits into, continued development of the amateur radio, of the radio art. Somebody said they wanted to do it, so they did it. And then they started selling it. Well, it's noon, and just a little teaser as to what tomorrow's going to be. Or I can actually draw this. P equals I times E. And those two things have a name. What are they called?
Ohm's law.
Ohm's law.
Ohm's law. Yes. And tomorrow we're going to do circuits. So we're going to have batteries with plus and minus, and we're going to have wires and resistors. And we're going to complete the circuit and figure out, here's our voltage, and here's our current flow, and we're going to be doing all kinds of calculations on Ohm's law. And then we're going to jazz things up a little bit by, instead of using one resistor, we're going to add a second resistor, and then maybe we'll add a resistor over here, and maybe we'll add a resistor over here, like that, and we'll do things that are in series and parallel. And then we're going to add like a meter across it to see what the voltage is, like this. And then sometimes we'll break the circuit and we'll put another meter here, which is with an I, that's called an ammeter. And we're going to do all kinds of fun stuff with circuits tomorrow. And then we'll get into schematics, which will contain things like what we just drew. And then we'll also do something like this. Anyone know what that's called?
Is that a transistor?
That's a transistor. We'll be doing transistors, and we'll be doing diodes, and we'll doing special diodes called LEDs. And then we'll do applications of those things. Like, now that we know that, what is this thing called again? What kind of wave is that called?
Sine wave.
And it goes through a positive side and a negative side. We'll be doing voltage sources that are always plus and minus, and that's known as DC. But then we'll also be doing things where the voltage goes like this.
AC.
And that's known as AC, which is alternating current. And AC, the fact that most AC current looks like that. And because it goes plus and minus, and diodes only conduct in one direction, we'll be able to do cool stuff like making power supplies and understanding why things like that work. And that'll be tomorrow. All right, you guys.
Same time, same station tomorrow?
Same time, same place. Does anyone have any questions? Now's a good time to ask.
Scott, what was the competition?
CQ WPX single sideband. And it's a worldwide thing, a combination of domestic and international contacts.
Is it similar to Field Day, which is in June?
Well, I mean, all contacts are similar. I mean, all contests are similar in a way, but this Field Day is a get outside and do stuff outdoors with your local club or by yourself in a remote location. This is, get on and see what you can do in a weekend. It was 48 hours. I only did 10 hours. I mean, only 10 hours, but it was, in my particular case, the fact that I made 170 contacts was kind of an amazing thing. Last year, I think I managed 50 in that same period of time, just because running low power and the bands weren't particularly good. The winners, if you want to see who's going to be the winner of something like this, to give you some idea of how serious people can get. I mean, this is the part of ham radio known as radio sport, which I really like. I've always enjoyed competitions and gaming and stuff like that. I don't really do a lot of gaming anymore because there's no time, but I do enjoy getting on the air. And notice of these 712 stations that have bothered to submit scores here. So here's little old me with 171 contacts and 44,000 points. And then you get your multi stations, which are multi-operator, multi-transmitter, people in either one place or distributed remotely. Notice in a 48-hour period, 5,647 contacts and 28 million points. This was S58Y that was in Slovenia. P33W, I actually worked them. That was a highlight. That's on Cyprus in the in the Mediterranean. 7,900 contacts in 2 days with one transmitter, multi-operator, but one transmitter. And here's another one. N7JI. I talked to them on like 3 or 4 different bands. 8,500 contacts in 48 hours. And here's a breakdown. Notice on the 10-meter band, over 2,400 contacts. So, here are the operators. They had a different operator on every band. And actually, I know 3 of them. So,
what would happen if you put a ham radio inside of a microwave?
I don't know. My guess is that the metal inside it would cause would probably damage the microwave. And secondly, all that RF energy that managed to get into this would probably start destroying some of the transistors. And the other thing is that what ends up happening is, and this is why they say never put metal in a microwave. So I'm going to draw a microwave oven. Right. I love questions like this because they're hypothetical, but at the same time, not really. All right. So this is a microwave oven. And what did we say the wavelength of a microwave is in a microwave oven? About 12 centimeters. So, okay. So this is actually a kind of a special thing, right? This is actually a resonant cavity where the reason that a microwave works is that your voltage on all the walls of a microwave, and this is going back to when I was in college, is 0 volts. And that way, what happens is you don't get any current flowing along the walls or along the floor or the ceiling or anything like that. So you have 0 volts everywhere, which means that if you have 0 volts, your sine wave has to look like either this, it has to be 0, right? Or it could be this. See if you agree. It could be this one. Right?
Yeah, I would
It
agree.
has to be 0 at all points. If I were to draw the vertical one, it would have to go like this. It has to be 0 on the top and bottom. And going from the front to the back, it would have to be like this.
Okay.
It has to be 0 on all sides. Okay? So, but it's in 3 dimensions, which means that on all the sides, it has to be the same size, which means that the sizes of the cavity in the microwave oven have to be of a couple of different sizes. They have to be multiples of wavelengths, either a half wavelength or a full wavelength, which determines the size of the microwave, which means that you can't just pick any size microwave that you want. It has to actually be, when you build it, it actually has to be certain sizes only that are defined by the wavelength of that wave. And those are the only sizes you can make a microwave. But now let's just say I pick some random spot inside the microwave. What is the voltage going to be going this way and this way and this way at that random spot?
Wouldn't it have to be still 0?
No, it's inside.
Well,
the only thing that I said is that the voltage has to be 0 at the top and 0 on the sides and 0 on the front and the back. What is it inside? In fact, it can't be 0 because it still cooks your food, right?
Yeah.
So it has to work. So what is the voltage at some random spot? It could be 0, but it's probably not. But what if I picked another spot? It could be 0, but probably not. But are they going to be the same? Probably not. Right? They're probably not.
Okay.
Okay, and if they're probably not the same, what we're going to do tomorrow in Ohm's law is E equals I times R. And R is resistance. And E is a voltage. And if I have a voltage here, E1, and another voltage, E2, if they're not the same, what does that mean? That they're going to be different from each other. And if I have, let's say, 11 volts here and 3 volts here, I have 8 volts difference.
Yeah.
And if I have, let's say somebody accidentally put, notice I say accidentally. Somebody accidentally put a knife in the microwave. Accidentally.
Yeah.
Don't do this.
Because
you're going to be responsible for buying a new microwave, right?
Yeah.
And somebody's going to have to put out the fire. What'll happen is, what is the resistance of a knife? What's a knife made of?
A knife is made of steel.
Steel, usually stainless steel.
Yeah.
And what is the resistance, electrical resistance of a piece of steel? It's almost 0 ohms.
Very low.
Very, very low. So we're going to draw that same circle, EIR. Okay. My voltage here is, let's say, 11 minus 3 is 8. And my resistance is going to be about 0. And we're going to
Yes.
cross that out. So my I, which is my current, is E divided by R, which is 8 divided by almost 0.
So that would be
What's something divided by 0?
something divided by 0 is 0.
No, it is not.
Oh, it's 1. It's 1.
Undefined.
It is undefined, and it comes close to infinity. In other words, as much
What?
current as you can have passing through.
You can put 0 into something as many times as you want.
That's right.
And infinity isn't a number, so.
Right. So what's 8 divided by 0.001? That's
It's like-
8,000.
Yeah.
What's 8 divided 0.001 is 80,000. So the closer this bottom one gets to 0, the bigger this gets. So so what will happen is that knife will all of a sudden be carrying basically as much current as the microwave can produce.
Yeah. So
Which will cause it to get really, really hot. Which will cause it to blow up burn up the microwave.
Yeah.
And that's why we don't do that. That's
Yeah.
why you don't put metal in a microwave, because you get immense amounts of current that will cause the microwave to catch fire.
Yeah.
So it's the microwave that gets hot, not the knife?
Correct.
No,
Basically, what
Isn't-
happens is that the knife will get hot and it will make it'll heat up the inside of the microwave and make it catch fire.
Okay.
Hey, Scott.
Yes.
Unrelated. So would you say that for this first lecture, I'm a textbook learner as well. That just helps me solidify everything. Did we get to about page 38 on the PDF?
Let's see. Where did we get?
Or do you would you know the numbers of pages we went over?
Yeah, give me a second. If I can remember where I was. There we go. I would say we went through on the PDF.
Mm-hmm.
We went through starting at 39 and went through 49.
That's the that's the electronic pages. The printed pages will be left.
Yeah. That's
Yeah,
on the
the difference on that is just that the electronically it's counting the introduction pages
Mhm.
that are not numbered.
Right.
And the PDF is actually starts counting when you get into the actual work.
Yeah.
Hey, Scott, I have a question that's unrelated as well.
Yes.
Well, cool. Thank you so much for the help. I'll see you tomorrow.
Yeah, cool. All right, go ahead with the question.
Class is over, so
yep,
maybe
you
I
feel
can
free
ask
to.
this.
Everyone can feel free to go unless you have questions or want to hear what we're talking about.
I'm one of those guys that, I don't know, 30 to 50 years ago was really into CB radios.
Yep.
And I'm just now got a ham radio, some handhelds. My wife and I actually bought 10 of them to give to all of our married children for emergencies because we live a ways away from each other. But in some of this that you were talking about today with the frequencies, and it reminded me on my CBs, the more expensive radios that we had, the normal cheaper ones didn't, but the more expensive ones had upper and lower side bands.
Yep.
And I always just assumed that it was like halfway between channels.
Nope.
But is it really more just that you're going, you know, like you said, they're offset on the frequency a little bit?
Nope. Here we go. So if we were to draw the frequency spectrum, we're going to cover this too. Here's our center frequency.
Mm-hmm.
AM looks like this. That is an AM signal. So you have your plus a little bit and your minus a little bit. So what happens is that you have your carrier. And you have because it's on the upper side, you have your upper sideband and your lower sideband. Right? Those are your different parts of it. So here's your carrier. And here's your upper sideband and your lower sideband.
So the carrier is like the channel, basically?
The carrier is the center frequency. And inside a receiver, the carrier provides energy for the receiver to generate the audio.
Okay.
But because it's just a single frequency and amplitude right here, it has no information. It just basically provides energy.
Okay.
Okay. So because of that, let's say that if you have, let's say 1 watt total being put out, this would be 0.6 watts. This would be 0.2 watts. And this would be 0.2 watts. All right. So you have all that energy. You have 1 watt spread out over this entire range, which is about 6 kilohertz. So your power spectral density of your information is actually quite low. You have 0.4 of a watt total spread out over 6 kilohertz. So it's like 0.4 watts over 6 kilohertz. So you're in other words, the amount of energy that you have actually transmitting information is really quite low. Now, what we can do with this is instead we can take that same amount of energy and we can look at this signal and say, okay, what do the sidebands do? Actually, the sidebands are they're what contain your voice, but the upper and lower sideband are mirror images of each other, and they contain the exact same information. So just from the standpoint of if they have the exact same information to you, do you need to send both of them?
No, you wouldn't.
Nope. So what we're going to do is we'll pick upper sideband just for the heck of it. And so what we'll do is we will take the lower sideband, and before we put it into the amplifier, what we're going to do is we're going to just wipe it out.
So then that gives you more wattage on the
well,
upper
now
side.
here's the next step. That would be a suppressed sideband. All right. But now let's say that instead of putting out that carrier signal, we can also do a trick where we eliminate the carrier. And inside the receiver, we generate something called a beat frequency right here, where we generate energy right here at what would be the carrier frequency. And we inject it at the receiver into the signal. So there is actually some reference point where there's the ability to generate to use this and to make audio out of it.
Okay.
So now we have eliminated the lower sideband and we've eliminated the carrier. How much of that 1 watt can we put into the actual information?
The whole thing.
The whole thing. So now, and how much space? What's our bandwidth? Instead of 6 kilohertz, we're only half of that now. So now we're at 1 watt over 3 kilohertz.
Over 3.
So that would be 0.4 divided by 6, which is, let's see, 4 over 60. So that's like 0.6 watts per kilohertz. No, that's not right. Yeah, that is right. 0.6 watts per kilohertz. And this is no, that's not right. Oh, 0.06 watts per kilohertz. There we go. And this would be 0.33 watts per kilohertz. So now when we get to the receiver, the question is, which one has which one has a higher density of energy in the actual information going across? Sideband is going to be roughly 5 times more efficient power-wise at getting information across. The other thing is, go ahead.
Oh, I remember from back then, I think 5 was the legal limit for a CB.
4 watts.
Right?
4 watts, yeah. Or 12 watts PEP. I think it's 12 watts PEP on single sideband.
I remember some of them that we bought. The guy that we bought them from said he had boosted them to 7 watts.
Yeah, I can't do it.
And he told us that he had, and it wasn't legal. Well, he said it wasn't
it's
legal.
Not, no, it's not legal.
But he had done it to the radio that we bought. So. Okay.
Yeah. But and you know, here's the other thing. Going from 4 watts to 7 watts is like pointless.
Really?
It really is.
Okay.
I mean, the other thing we're going to get to is doubling power is a change of 3 dB, which is a half of an S unit,
Okay.
which is nothing.
Yeah,
I
the
mean,
decibels I understand better than
yeah.
the
And we'll be
units.
getting to that, I think, tomorrow also.
Okay.
So, yep, that is largely why. And that's why like basically this is single sideband suppressed carrier. Now, the other interesting thing about single sideband is that let's say that you have a signal that looks like this, right, with no carrier. If you wanted to share a frequency, what could you do on the left-hand side of it?
Guess something totally different.
Something totally different. Yeah. So what it allows you to do, if you want, is have somebody else operating on lower sideband, and you basically don't really interfere with each other.
Right.
So you could be on the same channel. So right here, this defines the channel.
Yeah.
Right? Because CB is a channelized service.
But you're filtering out the one side or the other.
That's right. You're filtering out the
focusing all
unwanted
your
sideband.
energy on.
So really, they could be, sharing that same frequency and not interfering with each other.
My brother and I both used to snowplow in the Salt Lake Valley,
Mm-hmm.
and we'd be from one end to the other, might be 20 miles apart, and yet we'd still be able to talk to each other when we used the sidebands.
Yeah, and that's
with
why.
those radios.
That's why, because it was a lot more efficient.
Were there laws related to this sideband? Because we had one day when some guy got on and he kept telling us that you should not be on sideband. You're not supposed to be using the sideband.
Yeah, that's not true.
And I'm like, I've never heard of that.
No, that's not true.
So, okay. Yeah. All right. You answered
That's
my
just
question.
that's just somebody puffing out his chest.
Yeah. All right. Thank
Your
you.
drawing, on your drawing there of upper and lower sideband, what's the limit, upper and lower limits of your frequency there?
So if I were to draw that again, it looks like this. So if here's my center frequency, and I have something that looks like this, which really should be mirror images of each other, so like that. Typically, this is plus or minus 3 kilohertz.
And that's kind of a FCC defined.
Yeah, yeah. I mean, I mean, I've seen signals that go a little bit wider, but the standard is depending on where you are, 2800 to 3000 hertz. And what's nice about that is that if you're doing voice, I mean, a voice profile is going to look something like this. If it's a female voice, maybe it's a little bit higher, frequency wise. If it's a digital signal and it actually uses the entire band, maybe it's, fairly peaky even out to the end. I mean, basically at this point, we're looking at audio pass bands and how much the signal spreads on the audio. This is a direct translation of an audio frequency. So basically adding an audio frequency to a carrier frequency.
On a different subject, AM being amplitude modulation and FM being frequency modulation. Do you mind drawing those two on the same page, please?
Oops, that was ugly. Let's try that again. Here's AM. So you have your center frequency, and AM basically looks like this, where you have a carrier, and there's actually energy right there. And FM, right, and the amplitude as you go outward determines how much signal there's going to be at any given frequency. And FM also has a carrier frequency. And what you're going to end up with is something that spreads out. and it might vary in amplitude somewhat, but what ends up happening is that the frequency differential, the frequency of the voice, is going to cause the carrier to drift around. And what you're going to end up with is a whole bunch of different frequencies in here where they're going to be largely the same amplitude. So this is, and on AM, this is about 6 kilohertz. On your standard FM that most people use, this is about plus or minus 5 kilohertz. So it's about 10 kilohertz wide. Now, where this comes into play is that the math that governs this is completely different. And what happens inside an AM radio is, let's say that there's a lightning strike, and it takes the entire signal and temporarily moves the whole thing up. What ends up happening is you hear a click or a pop or a crackle. If this happens in an FM radio, you're not looking at the amplitude of anything, you're looking at the frequency. So the whole thing comes up. And what happens in an FM radio is that you typically will, before you even listen to it, you'll actually cut the top off. And you'll basically just look for a range of frequencies that are in it. So because everything is raised, by a lightning strike nearby or something, the crackle, you don't actually end up hearing it because it occurs on all the frequencies as opposed to just one. And that's why FM is much more immune to noise, like static crashes and things like that. AM is kind of like a natural thing. That's the way that the universe works. FM is a construct. Nothing in nature really is FM. Does that make sense?
I have a quick question.
Yeah.
Yeah, it's my understanding that everybody's supposed to broadcast on ham radio in English. Is that true?
Nope.
No?
Nope.
Okay.
You have to identify your station in English, and that's it.
Okay. All right. The reason I asked, I went to Hamtation over in Orlando a 3 weeks ago.
Mm-hmm.
I picked up a handheld and a mobile UHF and VHF, and I put in a local repeater,
mm-hmm.
and they were talking in Spanish. That's why it confused me.
Yep. No, in the United States, you have to identify in English. N7JI.
Okay.
Y después puedes hablar en español, puedes tener una conversación en español.
Oh, you must have been on.
O en français. Yeah. Yeah, I mean, you can. I mean, I've heard people speak. There's actually in Southern California. There's a very large Filipino population, and they have conversations in Tagalog, which sounds really weird to listen to, but they identify in English. I've also heard, a lot of Spanish, especially down, Southern California. And actually we have, a good number of Spanish speaking people up here who are in the club, and will actually speak Spanish on the repeater too. But you have to identify in English. Now, interestingly, I was in South America, and I had my my temporary license down there to operate. I could have a conversation in English, but I had to identify Charlie Echo 5 Diagonal Noviembre 7 J India.
Okay.
I had to give my call sign in Spanish, but I could have my conversation in English. I had to identify in Spanish though, per the country's rules.
What about when you're calling CQ? Does everything have to be in English then?
No.
Okay. All right.
You just have to identify your station per whatever the rules are, However often you have to identify in the language specified by the country that you're in.
Okay. Well, thanks for clarifying
And
that.
in the United States, it's every 10 minutes in English.
Right.
I see another hand up. Anyone? Is that it for hands?
Yeah, actually, I was wondering when the recordings of the lecture, I'm not sure if you mentioned it, are going to get posted.
I'm going to send it out to the list as soon as it is generated, and it can't get generated until I close the Zoom session. So,
No, I understand. Thank you so much.
Assuming it's still recording, which it should be. It says recording, so that's a good sign. All right. Any other questions? All right. See y'all tomorrow at 9. And by the way, Julia,
Yes.
are the kids still sane?
I don't know if they both are.
Okay.
I can check in with them.
But there's a lot of studying that has to be done on their own, on everybody's own. I can only do so much. I can help fill in the blanks, but by and large, you still got to do the studying yourself.
So what is your preference for doing the merit badge? Do you want them to work through the workbook or?
Yeah, I mean, the workbook is great. I mean, that's, if I mean, honestly, you get a license, that's 90, you'll be able to do 90% of the work.
Okay. Should they work on that first and then contact you to finish the merit badge part after going for the license?
However they want to do it. I mean, I think if you go through the licensing, the workbook becomes really easy. The more they get into it, the easier the workbook is.
That makes sense. I was wondering if having them try to write down answers as we go through would make sense, or to have them come back through that, or.
Well,
it seems like with a quick read through for the requirements again this morning, that they probably pretty much follow along.
Yeah. Okay. And I'm actually over at the, and you're in Eugene, right?
Yes.
Yeah, I'm over at the Eugene Science Center every Saturday too.
So would that be a good time for them to meet up with you when
That's
they're
a
finished?
really good time to do that. Yeah.
All right.
Although this Saturday I'm not going to be there, but
okay.
It could be Sunday, depending on how scheduling works.
Okay. We can try to set something up like that after we get through.
Okay.
All right. Sounds good. Thank you.
Cool. Anybody else? Thanks for being here.
Thanks a lot, Scott.
Bye all.
Bye.